Hi, Olivier.
Hello. So Romain should be coming soon for being a moderator. Grégoire is a technician from Work Adventure who has who's with us on the stage, and now we should be streaming live to the room.
Yes, the streaming has started.
Okay, so now we're waiting for the different co-authors to come on the stage. And we're also waiting for Romain to arrive.
Just Olivier, I'm sorry, I must to go. Don't hesitate to contact me if you have any problem or any need.
Yeah. Yesterday evening it worked okay. If we are already streaming, things should be okay.
Hi everyone. Well, maybe let me just grab my earplugs.
Okay, bye.
Thank you, Grégoire. So Romain will be the moderator of this session. Me, I'm more here as a technician to be sure the network will be working correctly. Romain?
Okay, sorry for that. Just had to be sure to avoid the echo.
So I switch off my camera and maybe ask the authors involved to switch on their camera, and me, I'm just here as a technician.
Okay, so I think I met with Majed, so on the map, so it should be here anytime soon. Yes. Maybe you want to try your slides, the sharing.
Yeah. I noticed something that my camera, it says unable to access to the camera inside the room. See, it was working well outside. So I might need to log out, like get out and get back again and test a different camera. I have 3 cameras connected to my computer, so.
Oh yes, I had this problem with I had also an external webcam, and in the end I had to use the webcam from my laptop.
Okay, so let me do that very quickly. Okay.
Okay, so we'll just wait for the speakers to be here to make the introduction. Right. So Reza, you're presenting for the Topogan paper, right?
Hello. Yeah, that is correct.
Okay. Yeah. Okay.
Yeah. And
Nice
shall
to
I
meet
do anything before or just waiting if there is any question I should ask?
So we would like to have speakers maybe do a short introduction of their paper, maybe 5 minutes, and then we will open the floor to questions. So we will do the first presentation, then maybe 5 minutes presentation, 5 minutes question. We do that for each speaker, and then this will leave like 10 minutes for shared discussion. And now we see you, Majed. So
Yeah.
Okay.
And
Okay.
the share screen, yes. So it gives me the option of 2 screens, which
Right.
works very well. So let me test. If I start the slideshow here. Oh, perfect.
Okay.
That one works well. Very good. Okay, I'll stop that too. Stop sharing.
All right. So thank you everyone for being here. So it's my great pleasure to chair this session. So we have 3 papers that investigate, let's say, generative design and design methodologies. So it's a session, I think, with little mesh optimization or post rationalization for construction. Maybe some topics that have been very active in the AEG community, but they ask a question about and propose solutions to design strategies. So we have contributions inspired by, let's say, ancestral gesture, like weaving. And we have contributions that are inspired by the cutting-edge technology like additive manufacturing, 3D printing. So it's very nice to have also this blend of inspiration and contribution. So without further ado, I will introduce the first speaker, which is who is Phil Harris from CETA. And he will talk about triaxial meshing with Kagome singularities, and will present a design framework to choose the topology of a lattice, beam lattice. So I leave the floor to you, Phil.
Thank you, Roman. Can you hear me? Super. And I hope that you'll be able to see the presentation now. I can't actually see that it's, yeah, okay. I'm going to go into presentation mode, so it'll take up my full screen. I won't be able to see the audience, but I hope it runs okay. Just give me a shout if anything goes awry. So it's a great pleasure to be at AAG 2020 or 2021 to present our paper, Meshing with Kagome Singularities. And I'm doing this also on behalf of the co-authors, GUN, Jack Young, and Alison Grace Martin. Just to give a little bit of context to what I'm presenting today, we had a paper at AAG 2018, also co-authored with Alison Grace Martin and Mateus, called Beyond the Basket Case. And in this particular paper, we were looking at establishing the principles, the topological principles that govern the inducement of double curvature in Kagome weaving. And finding a great interest in this because, of course, what we're able to achieve using this method is high complexity in double curvature, but only using straight strips of material in an interlaced configuration. And we feel that this holds great value for rationalizing construction if we can start to find strategies for being able to scale this up beyond the scale of baskets. So the paper that we're presenting today actually addresses one of the open representational challenges that remains in the representation of Kagome weaves. And this relates to the issue of being able to specify particular valences for inducing double curvature within a triangular representational mesh. What you're seeing here is our mesh topology adjustment scheme, which is the focus of the paper, and how it is that we're able to use this applied to planar meshes, also singly curved meshes. But the critical thing here is that there has to be some naked edges for this system to work. Sorry, I seem to have gone one slide too many there. So just to introduce the task definition for the mesh topology adjustment scheme, we can define this as the requirement of providing the means for introducing local valence changes in regular planar or singly curved triangular meshes at specific vertex locations whilst preserving regular valence 6 topology across all other vertices, with the exception of boundaries. So the way we achieve this is to use local mesh operations. Here you see that we're using the mesh edge flip. And if we see that our target vertex is the one labeled S, and we want to change this into a valence 5, we can achieve this by flipping that edge. The unfortunate thing is that by making a local change like this, we get unwanted collateral valence changes occurring around the previously connected vertices. So we see that rather than just inducing a 5 within a field of 6s, we now have 2 7s and a 5. Our mesh topology adjustment scheme deals with this essentially by looking at a region emanating from the chosen valence location and continually flipping edges out to the boundary. And you see that by doing this, we're actually able to embed now a single valence 5 within a field of valence 6s. And this starts to conform to the principles established for being able to create Kagome weave patterns. What's interesting is that we can repeat this same method for being able to achieve other valences. So taking a connecting edge to the valence will give us a lower valence, but flipping an adjacent edge will give us a higher valence. And again, to be able to embed that within a field of 6s, we chase these valence change, these edge flips out to the boundary. We can also extrapolate this then to actually cover all of the weavable singularities from valence 3 all the way up to valence 9. And you can see here how that begins to operate on the given triaxial regular mesh, and you start to see the regions that are being flipped in the colors here. And then through the relaxations, you see that we can actually represent exactly the same dynamics that are occurring within the physical weaves. Of course, from a design perspective, it's important that we can embed multiple valences, and the system does achieve this. There are certain exceptions, and the paper goes into those and describes some of the mitigation strategies for the issues that arise when we have interacting flip regions. But you can see that we can deploy this now to start to create quite complex weave representations. Subsequent to writing the paper, we've now been putting our mesh topology adjustment scheme in practice. We've been using it for being able to define also the fabrication information for weave systems. generating families of weaves and assessing these through other forms of environmental simulation. Also using this as a way of generating new kinds of grid for being able to simulate certain kinds of computational systems. And really all of these come together, all of these come together within our fungal architectures project, which is making use of the mesh topology adjustment scheme as a core tool for developing construction methods that are employing living fungal material as a computational substrate. So the mesh topology adjustment scheme is really finding tremendous value in pushing this work forward. So I look forward to answering some questions, and I'll stop sharing here.
Well, thank you very much for your presentation. It's really, really impressive and really quite beautiful also. So I don't know if we have some any questions from the audience. So if you want to ask a question, you can come on stage. And if not, I have some questions. Maybe a technical question on the mesh relaxation that you introduce. I was wondering how you do it and how do you constrain the strip to be flat in the end? Because it seems like the shape emerges from this your pattern. So I was wondering how you achieve that.
Yeah, I mean, very much so I mean, just to describe the kind of principles. The thing about Kagome weaving is that topology is king. Geometry is emergent through the interaction of the established topology and the material behavior as you move into the interlacing. And so we can describe geometry really as something that kind of emerges out of the establishment of that topology relative to the material properties and the interlacing that's going on. So, and this is why when you have a regular valence 6, you have in a physical weave, you end up, if you've only got hexagons, you end up with something that's planar. And the moment you introduce singularities, you're inducing double curvature, pushing things out of the plane. So in terms of how we do the relaxation in simulation, there's a two-step. Firstly, there's the simple relaxation in plane of the topology, so that we can actually embed multiple valences without coming across the issue of developing very skinny faces. And there it's just a regular relaxation to try and keep edge lengths equivalent. But as we want to move things out of plane and start to look at more fabrication-related information generation, such as what are the lengths of the strips, we want to embed in our relaxation the constraint that we are developing straight strips. And we do that through, we had a really nice discussion with Daniel Piker, who was helping us with some work with Kangaroo 2. And he pointed out that we could be using an energy goal looking at maintaining equivalent angles, because one of the interesting things, and I think you realize this also, or you acknowledge this in one of your papers about Kagome, Roman, is that actually the valence at the material crossings is actually 4, and it's consistently 4, even though we have reciprocal triangles and different valences here. And so we can do an equal angle relaxation that starts to give us the linear strips that define the straightness of the weavers.
Okay, yeah. Very nice. So I think we have a question from Professor Tachi.
Hello. Thank you very much for sharing this exciting work. It's really connected with this topology of with this Gauss curvature and the number of valencies. So I was wondering that if you can apply this method for closed surfaces, because, for example, a sphere must have like 4 singularities for like 12 singularities if you use 5 points, and then but currently you are applying one by one. But if you take, for example, one vertex turn into 7 and one vertex into 5, if you put it by pairs, is it possible to obtain a surface that is somehow possible to be achieved, or it's
I think one of the issues is that we need to be able to chase valence changes out to the boundary, I think that we may need to be thinking about a different approach if we're looking at closed meshes, because of course with a closed mesh you haven't got a limit. Things would just keep wrapping around and constantly changing your edge flips. So maybe there's a little bit more intelligence that could be put into the scripting to try and maintain maybe histories of edge flips. We haven't quite got that far, and at the moment, in terms of our application, having dealing with meshes that have naked edges is quite useful in terms of creating enclosure. But I think from a kind of more generalized representational perspective for this kind of work, being able to deal with closed meshes would be really a next step. I mean, Jack Young, one of the co-authors, when we were doing this work, had some interesting propositions about how we might be able to achieve this. He was actually questioning, why is it that we begin with a regular mesh and look to introduce valence changes within it? So essentially introducing the defects. One way to think about that in different terms would be to actually create a graph of all of the singularities in the first instance, find out how it is that they connect, and then do a loop subdivision, which would actually then fill with triangles. So you'd actually fill then with when you take the dual mesh, you'd end up with the hexagons that you need to then create the weave pattern. So I mean that's something that I think is really worth a little bit of investigation, and is something that we hope to be doing in the near future.
Sounds exciting. Thank you very much.
Thank you. So yeah, very interesting, and it reminds me also of the work of Robin Oval on topology finding, but for quad meshes. So it's maybe there is something also to to kind transfer, I don't know, from what he has done on the quad meshes to these triangular meshes.
Absolutely. I mean, I think one of the it seems to be one of the limits in transferability that seems to be immediately there about the dual colorability, and of course that would pose an issue with something that is essentially hex based. But I see in a paper that you're also a co-author of. Together with Olivier.
Disclaimer.
There are some really nice methods for being able to actually move around those kinds of constraints. So things like dealing with odd numbers of valences. So there seem to be some quite smart workarounds. And I just wonder whether there's also a way to start thinking about the dual colorability dealing only at the crossing points, because there you only have ever two members crossing, I mean, this is also the same point that you make in your Kagome buckling paper, that essentially you can look at them as similar kinds of construction techniques at the point of the crossing.
Yeah, the connection is the same as a quad mesh. Like it's if you look just at the node, it's the same. It's the same thing. So
Exactly. Yeah. I mean, the only thing that I would say we're trying to preserve is the idea of interlacing. So the reason why that is interesting is it would allow you to not have to deal with connections at every node, because you're essentially dealing with member-to-member friction. And connections then only need to exist at the boundary, which is a great saving on connection cost, but also has a wonderful ability for a kind of design for disassembly, because then you just take your boundary elements away and you can always take the unweave your members. Of course, the kind of the trade-off is that you've got to deal with very weak members to be able to have local flexibility to actually achieve the interlacing. That's something that we're still struggling with.
Yeah, great. So yeah, there are many questions. I think we have to carry on to the next paper. But thank you very much, Phil, for the very interesting discussion. And the next paper was on TopoGAN, so topology optimization with generative adversarial networks. So a paper dealing with machine learning, and Reza was here at the beginning of the session, and I don't see him now. So maybe we will switch the paper. So I know he's around, but let me zoom out to see if he's in the room. Okay, so maybe I will waiting to find the second speaker. I will leave the floor to Majed Gergis, who has also a presentation on topology optimization, but related to 3D printing. So we jump from weaving and millennial technology to something from the 21st century. So I'm happy to leave the floor to you.
Okay, thank you very much. And let me start sharing my screen for a second. Can you all see that? Okay. So good morning, everyone, or bonjour in France. And my name is Majed Gergis, and I'm here. I'm super excited to present our latest work with Shane Principe. I'm an assistant professor at the University of Tennessee in Knoxville. I'm a professor of design and structural technology, and also I'm a director of a Soft Boundaries Lab. Soft Boundaries Lab is a multidisciplinary research lab that investigates the intersection between architecture, science, and biology, and biochemistry, mathematics, discrete mathematics, and differential geometry, and robotics. Our current research focuses on the development of really high-performance integrated structure system using large-scale digital fabrication, robotic fabrication, and additive manufacturing. Prior to joining UT 3 years ago, I was a designer with Skidmore, Owens & Merrill in Chicago, where I was part of the Black Box group. I was a design researcher with SIM Foundation and worked with Bill Baker on multiple projects. So I'm really excited to present today's paper, which is the biomimetic generative morphologies for 3D printing. the idea is that there was a really breakthrough in the recent development of both computational form finding and additive manufacturing. We, in this research, will try to investigate the potential of which topology optimization in particular and additive manufacturing can extend the boundaries of the current application. The urgency of that research came from the idea is that our current construction or traditional construction system uses, we call it subtractive, because you always trim or cut pieces and then you to the part that's usable part. That produces almost in 2015, it produced about 500,000 tons of waste in the United States, and about 61% of that came from non-residential, where almost 40% come from residential construction. The reason is that so I really like that image. The image on the left, this is from 1877. That's a timber frame. And then the image on the right is just a recent image of the same construction. So it's almost 140 years where we haven't really changed the method. It's a very successful method. It works on repetition of the system. That will give it the structural integrity. But it uses a lot of material, and we were wondering, the question were asked, if we were to optimize these framing, these faces, what we get. And on the other hand, if we compare the subtractive methods of traditional construction to additive manufacturing is as you might know, or known as a 3D printing, is an additive layer by layer, waste-free system, right? It can create a complex geometry directly from models. The idea is that additive manufacturing until recently has been limited to small prototypes or like large-scale prototype, but it's still in a really nascent stage. Some of our early work, we tested out large-scale additive manufacturing, using reinforced carbon fiber reinforced ABS. This is a video, a time lapse out of 15 hours. It's in 30 seconds of a 3D printed building components that was printed as parts, were then later assembled on site. So the idea here is that large-scale 3D printing for building components, it's actually approachable, but we have to reach it or approach it in a different ways. This is done in collaboration with Skidmore, Owens and Merrill Beauty and Oak Ridge National Lab, and this is Clayton Home facility. So these are some of the images of the assembled final models. But then the final prototype was designed to actually be paired with a also 3D printed car, and both of them has like a symbiotic relationship where the enclosure can power the car, and the car has a hybrid electric engine that can power the enclosure. So in theory, it could be off the grid, and they have to co-depend on each other. That will bring us to how we push that research further. We, as all of you might know, that topology optimization basically is a computational form finding method that can determine the best possible forms based on material optimization or distribution within discretized design space. That's introducing like basically load boundaries and so forth. So the idea is that topology optimization is not a new topic. It's been really changing industries like automotive industry, aerospace, and resulting from 20 to almost 40% of material reduction. Similar principle of topology optimization we can find it in nature. So the image on the left, this is the bird bone tissue of a starling skull. The image on the right, this is actually one of our work that we were testing about generative morphology of topology optimization on a three-dimensional volume. It's the same method happens in nature, where you optimal use of weight to rate ratio or strength to weight ratio for efficient use of material resources. So during that research, we looked into test different multiple workflow. I'm gonna walk through them very quickly. The first one, we wanted to test out, first we tested the 2D topology optimization, and then 3D topology optimization, and then we will run a finite element analysis on the parts to test out if it meets the criteria for the initial testing, and then finally creating the workflow for robotic fabrication. So the 2D topology optimization provide a really efficient way of creating, understanding the topology optimized model. It's extremely fast, and you can make, like we did, like hundreds of these iterations to test out different load conditions, and made a massive catalog to learn that. It uses very low computational power, and it can give a good, quick representation of what's, like if you pay attention for this particular slide later on in the 3D model, it will be almost the same result, but more in three-dimensional behavior. So what we've done is that we created a small prototype of a house, and basically started breaking down every surface, and then we transferred the load from each surface to the next one while applying like two-dimensional planar topology optimization. That give us some ideas about where the stress is, where the principal stress, the location of where material needs to be, and then finally we assemble that model to do the same thing. Later, we took one of these panels, like we separated one of these, and to start to create a three-dimensional model representation of this one. So we start creating develop a mesh, and then from mesh we create a NURBS model, and then finally we had a 3D printed part. So in the previous work, we were using reinforced carbon fiber ABS. For this one, we wanted to test out new material. In this one, we're using a new material. It's biodegradable composites. It's a reinforced bamboo fiber enforced PLA that's developed by Takemer and ORL. And then the idea for that, you can take actually the waste that we initially used to be waste, and then you can recycle it again and use it for 3D printing. So then the next phase, we start looking into generative design, which basically it's three-dimensional topology optimization using the same exact principle, but in this case, we apply it in three-dimensional volume. In this one, later on, we would test it maybe adding volumes for programs. So these branches will start to avoid certain spaces. And then we tested the 3D printing behavior of that branching model, which one of the significant advantages of this workflow is that the final model requires virtually no editing. It's ready to 3D print. And what's remarkable about this is that the forms, or the organic forms of the topology, actually the optimized model, it's really resemble the bone structure of this bird skull, which is it's not a coincidence. Like Wall's law states that the animal bone varies in densities loads based on the computational form finding, which is the same principle that we're trying to achieve in this one. So to just summarize, the application of robotically controlled additive manufacturing is still in nascent stage. We will continue to develop this to a full-scale prototype, and thank you for your time, and I'm like open for any questions.
Okay, so thank you very much for your presentation. It's a really interesting work, and I don't know if we have questions from the audience. I have some some questions, and we had actually one question from the YouTube video. So it was a question from Elisa Ross. So I can read it if you want. So she says, thank you for this nice paper and presentation. I'm curious to know whether the 3D printing results validated to detect any difference with the simulated results. Did you observe any impact of the fabrication methodology on the results? In particular, I'm wondering about any fabrication introduced defects like delamination and so forth that may have an impact on the performance of the physical form and how your model might account for these.
Yes.
So big question about the 3D printing process. Well, which we know is not necessarily perfect. You don't have necessarily a uniform material, so you have kind of a trace of the fabrication process.
Right. That's an excellent question, and actually, one of the major reasons why we wanted to test out like topology optimization in particular is that in our early work in the additive manufacturing integrated energy, the full-scale printed model one, it started as a design. Like we started with a design, and we wanted to create these panels. There was a lot of constraints when you 3D print at that scale, at full scale. It's dissimilar from your desktop printer. A desktop printer, you can make support material and you can break the extra material. You can have the powder bed where you can basically 3D print with glue, and then the powder itself becomes the support. And then finally, you can have the dissolvable material, right? Which actually we're testing out these days, the same method. For this particular one, we kept the same constraints that the traveling angle before you start having delamination or basically the layers start to sag on top of each other for any cantilever part. For our initial test, when we got the specification of the BAM printer with the big area add manufacturing, they said it was 45 degrees. But actually, on the real testing, it turns out any angle that's more than 25 degrees, it will actually have delamination and stuff fall apart. It's because at that scale, it needs support beneath it. So anything that traveling angle that's less than 25 degrees, it will have delamination. So the 3D printed prototypes that we tested for this particular model, we wanted to test multiple things. First, we need to have either minimal or no support material. So basically the model, you can call it self-supporting model. And what happened is that the branching or tubular form of this topology optimized model resulted in a self-supporting geometry that actually doesn't require any support material. And the way we do it, we actually print it upside down. So the model itself is generated by tracing the load through, so it's almost like a branching tree. But if you want to print that tree, you want to print it flipped. So you start taking the largest part, and then it will start to branch to the tiny parts. So actually, I have a short video toward the end of the presentation that can maybe explain this a little bit better. Let me see. So if you go to, yes, so if you look here, it's the model always shown as the reverse. So in reality, the support is actually at the top here, but we printed it upside down. So and this way, every layer supports the layer beneath it, and the traveling angle never exceeds the 25 degree point. Sometimes it happens, of course. That's why we need to tweak the model every once in a while. But yeah, so in the earlier tests, it seems that topology optimization worked very well for to address a lot of this issue of large scale 3D printing.
So very ingenious to flip the design for better printability. Well,
that also adds to the strength.
It looks simple when you mention it, but it might take some time to have this idea. I think that Phil has a question. He's raising his hand. So
thanks very much for a really interesting paper and also and presentation. I was interested in the fact that that the precedent that you're looking at with the balloon frame, of course, that structure is also providing an opportunity for environmental enclosure and cladding. Although you're kind of claiming that you get a material reduction in terms of the structure that you develop, it seems that it's perhaps a little bit more complicated then in how it is that you might actually achieve environmental enclosure. Could you just describe what the strategies are for that?
That's a really great question, because one of the things we thought about is that in reality, which also happened to the earlier project, that people thought that the building was printed out of the printer as one piece, right? And then when they saw it, they say, oh, that's not fully, it's actually every part, it was component based. So in actually our current research, actually one of the work that we're working on now, it's actually going under patent, is that in reality, the structure will be enclosed. Like you have two options: either you're going to express the structure, or this is like layers where it becomes an integral symmetry. So imagine your balloon framing. Now it's replaced with so you have the two choices as a designer. It's actually, this is one of the questions that we had in mind. We asked ourselves that when you design architecture in general, you have two types, right? Structure expressed buildings, similar to like the John Hancock Tower, right? That's a skyscraper. Or even if you have a house and you have a beautiful truss wooden beam or a log cabin, you keep the truss exposed. The other option will be to cover that, to conceal it with material and finishes and enclosures similar you're mentioning. So at the end, as a designer, your design decision is going to be really crucial to which route you go to. It's the idea for this one is that, can we do something about that really prime wood that being trimmed and subtracted and almost 40% goes to waste, right? As opposed to, can we use only minimum material? Even better, if this material already was waste material, that would be a really exciting thing to do, right? So that's it's something that we always think about. I think 3D printing building is not going to be like you print the building as a whole. Maybe you can do that maybe with concrete, but I think it's going to be really component based, where you can build it in a controllable fashion. There are more things that we can also incorporate, like we're testing 3D printing insulation, we're 3D printing, incorporating the conduits for electrical, plumbing, and really it's a kit apart. One of the earlier inspiration for that research was an article by Boeing where they said they 3D printed a part of an engine that used to be 100 parts, but it's 3D printed at one piece. It's already assembled. So we face similar issue in architecture. If you look at the wall assembly panels, you have so many pieces. Like how many of these can you reduce the number of assembly required? And that's what we're trying to do. Hope that answered your question. You're on mute, Thomas. Yeah.
Sorry. Thank you, Phil, for your question. Indeed, a very interesting question, very interesting answer. And there is I had this question about, do you want to make a statement with 3D printing, which might be, more the case of the second example you've shown, or like, do you think that that 3D printing could be kind of hidden, and so like you're not making a statement, and when people will just live in a house without knowing necessarily that components have been 3D printing. So I think you summed that very well. These two approaches, like maybe like the John Hancock and maybe like philosophy, and maybe like the Leslie Robertson philosophy, like hiding beautiful structures, but not getting in the way of other aspects of the project as well. And I also want to point out that I really appreciate that you, when you show a bone structure, you show a bird bone, because usually people put a human femur, and in the human femur you have a fluid inside, and so it's it's optimized also with an internal fluid pressure. So usually people are not doing that with optimization, topology optimization. So I just wanted to, it was very accurate also on this aspect, that bird bones are actually more I think the proper inspiration for topology optimization. So I also appreciate this, and maybe it's also a comment. I think indeed that the component-based strategy and the 2D module approach for me was really interesting, especially when you think about other aspects like transportation. Of course, like with a 2D module, it's easy to put it in on a truck, send it on the site, and assemble like planar elements. Where it's really something that people know how to do. So also, I think it's very relevant with that respect. So and it's also maybe more relevant with regard to how people design buildings. Maybe we think about shear walls, we think about like carrying horizontal loads, vertical loads, and we slice a house with planes basically. So So I think this is very interesting to kind of enrich this design strategy with topology optimization. Yeah, so I was, and you also replied my other question, which was if you wanted to integrate other functionality or performance metrics in your optimization and fabrication, like insulation, acoustics, or this kind of thing. So I don't know if we have another question from the audience. I'm not. Let me check the YouTube live. No question. So I think we're just on time for the last presentation. So thank you very, very much, Majed.
Thank you for having
very
me.
interesting.
Thank you.
And I will now introduce the last paper of the session, which is about yet again topology optimization, but here combined with machine learning and generative adversarial network, so GAN, for those who are familiar with that. So that the paper is named TopoGAN, and the speaker is Reza Kakoe, who is at ETH Zurich. And you have a double affiliation, right? And you're also from Lucerne University.
Yeah. Yeah.
So the floor is yours.
Yeah, thank you very much for the introduction. And sorry, I had a technical problem. I don't know that you recognize that or not, but just so okay. I'm sorry if actually I bothered you.
Well, we could switch the presentation, so it was fine. I was a bit worried, but
okay, great.
Good to have you back.
Okay, great. I got some nervous, so let me see. I have to turn off my camera, but I share my screen to show you the slide. So. Okay, can you see my screen?
Yes, we see the PowerPoint.
Perfect. So hello everyone again, and so as you can see here, today I'm going to talk about topology optimization for building facade with generative adversarial networks, or GANs for short. So my name is Reza Kakoe, and this work have been developed by collaboration of my colleagues. I'm not an architect, I'm a computer scientist. But actually, I help this work in terms of machine learning, generative adversarial networks, and this kind of things. So topology optimization was introduced more than 30 years ago as an analytic method to distribute a certain fraction of materials in a large design domain using finite element method. The remaining material has to fulfill certain boundary conditions like load, supports, while, for example, maximizing stiffness of a part. Topology optimization have been used, as you know, in several industries, but also there are some examples that has been used in building industries. For example, in around 2004, there were a few examples built as a scale of full buildings, like as you see here, Akatagawa riverside project, and also these Qatar Convention Center, of course, in Qatar. But the process of, as actually, although the topology optimization is a very great tool and can help us in the industry, in different industry, but the process of finding optimal topology, even for the simple load, is computationally very expensive and of course time consuming. And it is not embedded in the real-time feedback loop, and also during the design, even in the start point or the end point of the design. So to address these challenges, this long computational time for a single solution, we were wondering if a machine learning method, more specifically GAN, which has been introduced in 2014, could support the designer by learning from a large element of existing solution. We adapted a special type of GAN known as PIX-to-PIX, which is an image-to-image translation method introduced in 2016. In this model, there are two neural networks competing against each other until to generate a synthetic output. The generator, which has been shown here by G, the goal of the generator is like an art forger and tries to come up with a realistically looking photo of a shoes, or I don't know, a human face, or etc. And of course, given a drawing output or given a real photo of the people. And a discriminator that acts like an art inspector and tries to distinguish the real photos from the fake one. The fake one, I mean the ones has been generated by the generator. So in the beginning, both of these networks know nothing about how to their job, but after each round of training, both their weights are adjusted. I mean, the weights of the neural network are adjusted to a little bit better and a little bit better until to converge to some values. That being said, the model has been trained. So there are many applications of this kind of PIX-to-PIX. You can see here, for instance, translation of segmentation of the roads to the realistic photos. Or here you can see translation of day photos to night one, or a translation Google Map to Google Road, and actually vice versa. Or even from, we can translate images from actually a sketch to the realistic photo. So these are a couple of PIX-to-PIX example. So, but in our work, instead of shoes or converting day to night or this kind of thing, we choose a load-bearing facade vault as an element of the investigation. We focus thereby on the architectural design potential of the openings. You can see more details in this picture. As you see here, because of so the windows are not actually just placed between a grid of supports, but are prominently causing the exceptions that also give the building its characteristics appearance. So you see here, for instance, different kind of this element. So this in this slide, you can see the final actually output of TopoGAN. We call this approach a topology optimization generated by the serial network, as short to TopoGAN. So here, as you can see, the result seems realistic. We will see more details in the, later on, but this is the final result. We actually somehow understood that the TopoGAN can somehow assist real architecture for the schematic design phase, and of course in the early stage of design process. Our project, or the objective of our study, is 3 by 3 meter wall element at the resolution of 23 millimeters. A linear vertical load is applied along the top, and there is a linear support along the bottom. What is different in all the examples, I mean, in our training set examples, are this kind of opening, different sizes, their position, their shape, or the number of openings that we have in the design. And so we have to set actually create or collect this kind of a data set. In our case, we actually created the data set. So we wrote a Python script based on, actually we used a Python script based on an available library of finite element approaches. And in this case, we generated, as you see, this kind of training data. There are some voids and openings, and a Python script would be able to generate the output, I mean, this kind of optimized topology in around 1 minute. So, but what about our topogan structure? In our case, the discriminator generally in pix-to-pix example or in pix-to-pix implementation, the discriminator sees these pairs of images, I mean, both input and also the real output, which has been generated by the finite element method, while the generator only sees the opening and also learns over time to fake a solution which somehow resembles the real output. Of course, in the beginning, the performance of generator is very bad, but this result that you can see here is after training. So you can see this is somehow similar to the real output that the finite element approaches actually created. So these are some other examples from our training set. So you can see in the left side of each column the input, I mean this opening and void, and this is the result of topology optimization. I mean GANs-based topology optimization. So these are also, as you can see, the performance of the GANs in the right side. If you can compare these two actually output, the real output and the one generated by the GAN, as you can see, in most of the cases they are similar. But for instance, for some actually object that you see here, the GANs approach wouldn't be able to recognize them, or here, for instance, it couldn't recognize. But in most of the cases, actually, the GANs did a good job in this case. So here we were going to somehow evaluate the performance of our approach. There are a couple of methods. You will see more details in the paper. So for instance, of course, the visual inspection would be the first one, the pixel difference, constraint violation, and also the area fraction. So for the case of visual inspection, as we saw in the previous slide, so they are somehow similar to each other. The left side are from the finite element approach result, and the right side from our proposed approaches. So for instance, here they are quite similar, or for instance, here it couldn't recognize again the thin part of the design and this kind of things. And the next approach to evaluate the performance, of course, is to evaluate them by pixel difference. So it is, I think, very straightforward. We just actually pixel by pixel evaluate the performance of the topogan approach. And here you see the result. In this picture, in many cases, tree-like structure is just a little bit offset. So for instance, here, maybe this kind of red color shows that it should be somehow some support or some object here, but there isn't, and the blue is vice versa, actually. And this is about the constraint violation. One constraint enforced by topology optimization is that the red cells in the inputs are mandatory to remain. So as you can see, so you can see the red actually object here. And again, it is clear that the topogan could understand to avoid put materials on top of this red actually object. So it means that it's somehow without having know about them. So this is the beauty of the machine learning approach. It just learned from the data. And regarding the area fraction, so we so regarding the area fraction, we count the ratio of the black pixel to the total pixel and compare it with 30 desired area fraction specified in the topology optimization, I mean, in the finite element approach. And surprisingly, without actually told without we actually say the topogan explicitly, the generator network gets the right that area fraction ratio. So it means that the output of the generator again would be around 30% ratio, which is similar to the finite element approach. And of course, there is always a trade-off. The finite element approach are very accurate, but of course they need a lot of time to find the final optimization. But our approach in terms of precision is a little bit off, but in terms of time it is quite fast. So in a matter of seconds, it could generate the output. So you see here as an animation, we change the position of the opening, and you see here and in the right side the design of our topogan approach. So you can see that somehow it could follow the input perfectly, and also could design in a second the optimized design. So here we scale the opening, and you see the result on the right side. And then we change the proportion. And in the right side, you see the result again. And of course, change the topology of the openings. And it is, I think it's quite complicated because it's somehow distributed the openings around the facade. So you can see it quite, it is actually quite fast to find the optimized solution. And so I think I already talked about them, so I'm going to skip because we don't have enough time, I think. One of the main questions some might ask is that is our approach is creative? So of course we cannot say that it is 100% creative, but if you put this approach in the hands of a creative person, it could be incredibly powerful and produce astonishing, and as you see, very super fast result. And if it is intelligent, so of course the definition of intelligent would be very, I think it needs actually long discussion. But topology optimization was able to learn and apply hard numerical constraint like the opening constraint or the area fraction without being explicitly programmed for. And it can, for instance, replace the designer. Of course, it's a counter question. We should ask, should it? Of course, topology optimization may not embed original solution itself, but it can stimulate the architect's creativity, playing with constraint and discovering the consequences in real time. As you saw in the previous slide, it was quite fast. So this kind of fasting design could allow different workflow to somehow combine with this topogan approach. So thank you very much for your attention. And if you have any question, I would be happy to have.
Yes, thank you very much for your very nice presentation and very nice paper. So I don't know if we have a question from the audience. So if not, I have some questions maybe to start. So I was wondering if you tried different sizes for your training data sets and how sensitive it is to this parameter. Maybe you can recall how many simulation you need to achieve the results you mentioned.
Yeah. So for the different data set that we had, we of course trained the neural net for different epochs or different iterations. So for instance, the biggest data set that we had more than 1,000 training data set, and we trained the neural net for 200 epochs. It took around, I think, 1.5 hours, or our actually a GPU machine that we had, but just one GPU machine and 64, I think, gigabyte RAMs that we had, our machine had. So it was not that much high-tech technology or machine, but it was quite fast to generate and to train the neural to the GAN. And in the test phase, of course, as I said in the slide, it is quite fast. It's less than 1 second, and it's just at real time. You can real time actually propose the design and the optimized design. And of course, when we wanted to train the model, we of course put some data away for the test set. It means that the neural net didn't know about this test set as well. And also we had some cross evaluation. It means that we train the GAN for one data set and test it for the another one. And so the result, of course, in the paper. And of course, that one also is very interesting. We could reach out to the optimal design quite fast.
Okay, so I also really enjoyed the distance field that you use to kind of give more texture to the image, because well, I guess it's very hard to learn just black and white with very high contrast. So I was wondering, so here you took one load case, and did you consider you also learning for different load case, maybe, with this kind of strategy where you would, where the load is applied and, create a distance field? I don't know. It's just a question I have with respect to that, because obviously it would be very neat to be able, to put a force in a certain direction and to optimize the structure.
Actually, in our implementation, we didn't test different load or support strategy. As I showed you in one of the slides, actually the support are just in the bottom, and also the force on the upside of the design. So of course it could be a good way to further evaluate the topogam, but we didn't test that. Yeah.
Okay. Yeah, but it's really impressive. I think like this kind of technique has a bright future. I've seen some papers about CFD, which is also something very expensive to do, and people make this learning. So it wasn't with GAN; it was more like a simple neural network.
Yeah.
But already, like, the value for that is huge, because it's not something you can do in design procedure. So here you mentioned 8 frames per second, which is indeed, I think, we can call that real time.
Yeah, exactly.
And I was also wondering maybe about for people who are not familiar, how many layers do you have in your neural network?
Yeah, actually, we use the basic pix-to-pix implementation offered by the author. It had 8 blocks in both generator and also the discriminator for the encoder and decoder of the generator, and each block had 3 layers. And for the discriminator, it is rather the same. It consists of a couple of blocks, I think 7 or 6 blocks, and again, each blocks have 3 or 4 layers. It depends on the blocks that we have. Yeah.
Okay.
It's not that much deep neural net. That's why it was quite fast. So as I told you, in around less than 2 hours, we could train the neural net. So it's not that much huge network. Yeah.
Yeah, but sometimes it's better.
yeah, of course.
So yeah, and I have to say also, I really enjoyed the fact that you asked those questions in the end about like how this interacts. How should we feel about this?
Exactly.
And when you ask, is it intelligent? It reminds me of a book by Douglas Hofstadter, which is called Gödel-Escher-Bach. And in the end, he talks about intelligence and machines. And in the end, his conclusion is that we tend to define intelligence in a negative way. We say intelligence is what the machine cannot do. So when he wrote the book, computer were not able to beat a human at chess. And so he told, well, for example, people saying that playing chess is being intelligent. And he said, well, one day people will will be beaten by chess engines. Now it's it's done, and it's done for Go, and so I think it's also it's actually very hard to define what it is to be intelligent and creative with these tools. So I think it's also it's also stimulating for us, you know, so I think we should embrace all these technologies and you know, really think about what we are doing with it.
Yeah.
So,
that's quite true. Yeah.
So thank you very much. I think we're running out of time.
Yeah.
So maybe the next session I will close this session. I think the next session we will switch the orders of the presentation, maybe to even out the speech time for speakers. But I thank you very much for your presentation, the three of you. It was very, very interesting, and I think the discussion was very high quality as well. So if the members of the audience have additional questions, then you can just, you know, meet the speakers, and I think they would be happy to answer the question if you're a bit shy and you don't want to go on stage. So so thank you very much. And the next step, I think, is in 20 minutes. If I'm not mistaken, right? We will have 2 sessions in 20 minutes. So it's time for the break now. Thank you very much to all.
Thank you very much. I stop the broadcasting.
Hi, if the authors want to come on stage. Just to test the sound, maybe. Just before you come on stage, maybe you can turn your camera and microphone on.
Okay. Ouais, bah j'imagine bien, ouais. C'est vrai que là, c'est vous qui êtes venu.
Maybe Yuta, I see you're in the room. Do you want to come on stage to test the microphone and camera?
Ouais, tu vas pas repasser à Paris. Ouais. Ouais, bah ouais. Non, mais c'est sûr que moi, mes potes, je leur conseille pas de repasser, hein, ceux qui sont motivés, c'est un peu ça revient de temps en temps, mais c'est vraiment pas le bon moment.
Recording is on.
Hi. Do you want to try the microphone, all of you? Hi.
Hi.
Okay, this is working.
Is it working?
I don't know. Test 1, 2.
Yeah, and maybe Clara, can you try talking?
Yeah. Can you hear me?
For everyone. Perfect.
Cool.
We are already on YouTube. I started the live.
Right.
Should I try to share screen?
Yeah, maybe you can, yeah.
All right, the program is saying we should be in room A.
Should it be in room A?
Oh,
Yes.
really?
I'm not sure.
I think you're...
Let's see. Sorry about that.
No,
A.
it's B, I think. Hello.
Hi.
Oh.
Oh, okay.
Hi. Yeah, this afternoon you're going to be in room A.
Oh, so different room for morning and afternoon. Okay. Makes sense.
Did you manage to share your screen?
Oh yeah, I'll do that now. Okay, so how do I share screen and should see? Maybe here. Can I just share a window? Yes, I can.
Yeah, it works.
Works, yeah.
Okay, cool. Oh, this is slightly weird because I cannot see anything besides my PowerPoint presentation. Okay, but it's going to be okay. Can you hear me all right?
Yeah, I can hear you.
It seems that I have an unstable connection.
Oh, really?
Okay.
Is this already on the live stream? Oh, I can.
Hi, Dukes.
Hello.
Hi, Dukes.
Hello, good to see you. Can you hear me okay? Is my microphone working? Very good.
Ouais, je vois ça avec couverture réseau. Ouais, et du coup, ouais, ils sont pas des ingénieurs d'offshore vraiment.
So it must be super early for the guys in the US, no?
Yeah, it's 5 in the morning.
Wow, it's terrible.
Helmut, are you at KAUST or in
I'm
Austria?
at KAUST, yeah. No, I'm at KAUST now, yeah. I cannot really show you the view because it's too much sun. But there is a view to the sea here.
Oh, nice.
Shall we try to keep the presentations to 5 minutes?
Yeah, I think if it's slightly more, it's okay. But we definitely should give the audience a chance to ask questions. But from the experience of the previous sessions, there isn't too much coming from the audience, I think. So, yeah, it's really up to you. Yeah.
No problem.
I have some questions for every one of you. but I hope there will be others coming from the audience and among you, because I mean these papers are very strongly related in a sense. Yeah? So I think there could also be some questions among you. Yeah? So we still have 5 minutes.
Yeah, we are already online. If you, yes, I wanted to make sure it works, so we are already online.
Okay.
Thank you.
Okay, so.
Ja. Ich habe in 3 Minuten meinen Vortrag. Was gibt's?
Achso, nein, ich wollte nur sagen, der Lutz, der habe ich jetzt bestätigt und die liefern in den...
Rupert, you're not muted.
Also du müsstest nicht...
So maybe we should get started. So according to my watch, it's the right time to get started. So let me welcome all who listen to this session, which is largely around origami, curved creases, and so on. And I think we have 3 really interesting presentations, papers. with a lot of relations among each other. And I think it's a good idea if the authors get the chance to quickly present their work, because you may not have read this, the paper, or not yet seen their video, which are all very nice. So let me start with, I think Clara will present, right? And first paper, all three authors, if I'm not mistaken, are on stage. This is Clara Mundilova, who is now at MIT. She used to be in my group in Vienna. Then I see Rupert Malecek from Innsbruck. And I see, of course, Tomohiro Taki. So all authors are around. And I would like to invite Clara to give us a short presentation of this paper, and then we are going to discuss it.
Yeah, no, I'm not muted anymore. Sorry. Yeah, let me quickly share my screen. Can you see my screen?
Yes, yes, works well.
Okay, great. So thanks for the introduction, Helmut. In our paper, we propose a method how to turn a polyhedral surface into a rounded object with curved creases. And as previously mentioned, this is joint work with Rupert Malecek and Tomohiro Taki. So our method starts with a polyhedral surface with planar faces. And in the first step, we round each edge with the right circular cylinder so that it is tangent continuous with the adjacent faces. Then we consider each neighborhood of each vertex separately, and we find a good 3D and 2D apex position so that we then fold into cones and planes around a vertex. And so there's a certain design freedom for the depth of the vertex position. And so there are two non-trivial steps in this approach, which are discussed in our paper, namely, what is a good apex and how do we fold into a cone? And so a good apex, we identify a couple of properties that we would like to have. Namely, we would like the folds between a cylinder and a cone to remain developable, and the cylindrical surface to be the right surface. Then we also don't want the two creases on a edge to intersect. We would like the surface or the crease curve to be tangent continuous around the vertex, and we don't want surface intersections. And if you have more questions, please ask later, or please refer to the paper. Okay, and so unfortunately, these constraints forbid us to find good apex position for saddle-shaped vertices, which is slightly unfortunate. But the good news is that we also can find a method how to preserve developability. So if we have a pattern or a surface that would be developable without any cuts, like this chicken wire tessellation, then rounding would give us material loss. And we give a method that computes a consistent material loss so that the rounded version still remains developable without any cuts. We've implemented this approach as a grasshopper component that looks like this, and we also offer a GLL that can be used in a C# script to offer the designer more freedom for the design. That's all. Thank you.
Thank you very much, Clara. Thank you. Any questions? I mean, she left a lot open, of course. We can also ask her to go into more detail. So, Clara, let me start. Yeah, you said maybe you should explain here hyperbolic vertices, so non-convex vertices, saddle-shaped, are not working. Is this because the cylinders are on different sides, or what is the main obstacle there?
So we don't want self-intersections of the surfaces, and this means that the surfaces, like the cylinders and the planes adjacent to a 3D apex position, need to be visible from this apex position, like in order to be folded into a cone.
Different sides, yeah.
And so this, together with constraints that come from the valid patch condition, like for good crease curves that I didn't talk in this short presentation here, together this amounts into constraints that do not work for cell-shaped vertices. Tomohiro, did I miss anything?
Oh, so it's actually possible to make hyperbolic surface that is containing like half sphere. So if it's wrinkled very much, so it's not intrinsic property that is used, but it's more extrinsic property that you cannot contain the surface on some hemisphere. So for that's the impossible case that we found out.
But locally, a real hyperbolic surface is not on a hemisphere, right? On one side of it.
Well, if you think about smooth one, yes.
Right. Yeah. If it's badly resolved in a sense by a discretization, then it could be. That is true. Yeah. Yeah. Sure. I agree. Yeah. So I liked. I mean, you had this bunny around, right? Where with these holes, and all these vertices obviously have been convex, right?
Yeah.
Yeah. So I liked most actually the ones where the smooth parts, the cylinders and the cones made up the biggest portion of the surface. So I found this somehow more interesting than. Do you have some insight how to, or do you know how far you can go, yeah, or how to design something where only very little is left from the plane? So in fact, you have a kind of more smoothly appearing or a more curvedly appearing model. Do you have some insight on that? And, yeah.
Good question. So the current implementation as a design tool only allows experiments, and like there you can check how far you can go with the rounding of the edge, so that it doesn't do anything bad. Yeah, but we haven't investigated like the constraints for that. But I assume that this would result in a global like optimization where you just like try to make each cylinder as big as possible. This is probably something that we could consider. Thanks for pointing out.
And when you have this model like Sabani, of course, you need to introduce cuts, right? There's no way that there's a flat sheet and you, yeah, sure.
Yeah.
And so for me, the following question is totally unsolved. Namely, if you have really a free-form surface and you would like to approximate it with a curved grease surface, not with this pleated pattern, which we had, this we know very well how to do, but with just, let's say, a few curves, does your insight here, your approach, give any insight? I should put it this way. Do you have any insight on solving this problem? Why is it just a totally different problem?
We are actually kind of trying to make this freeform surfaces through curve folding. But the idea is that you have to have, in some part of the surfaces have more wrinkles, and some part of the surface that is less wrinkled, in order to get totally globally non-developable surface out of single developable surface. So it's again very similar to the problem of making any form out of sheet of paper. It's possible theoretically, but might result in for some part, it might result in a lot of wrinkles around. So it's quite difficult to design, but yeah, we are trying to.
So you talk
test.
about wrinkles. So I was talking about smooth things. Yeah. So you have a sheet, and you mark nice curves, and then you fold up, and then you get as close as possible, yeah, to your target shape. You may miss it quite a bit, of course. This is clear to me. But I'm not thinking of, I do not know which wrinkles you mean. Could you tell me where the wrinkles are?
It's about, well, it's when you have a crease of going up and down. So if you increase the number of these
creases, yeah.
If it's curved, so then that what is more allowing. But now, so you have to distribute these material shrinkage in order to get the non-developable. So if it's globally, it doesn't have a extremely large.
Since I have it in my office, I do not mean this. Yeah, this was from our previous work. I mean, just a few curves. And this is what it's usually very aesthetic design. So I find you just have a few curves and you get some interesting designs.
Yeah.
Anyway, so I do not see questions here in the chat, or maybe I am not sufficiently familiar with the whole tool. That is also possible. Clara, do you have ideas beyond cones and cylinders? Would this be something doable?
Do you mean like for the polyhedral surface, or for
not necessarily, but some nice design tool? I mean, for me, this is this broader idea of designing something with some curved creases. In your case, also some cuts, which is okay.
So thank you. So currently, I'm working, or we are working on a software that is again a grasshopper component, or a set of grasshopper components called Lotus, that allows the user to fold a arbitrary developable surface into a cylinder or a cone with specified 3D apex or ruling direction. And hopefully this will be published soonish. And so, we would be interested in also finding more general approaches to then fold into like tangent developables, but this seems a little bit harder. So we are also looking into some approximations of this like second surface that we find the fold in. So
I have one question, this connection, because so I think but maybe I'm totally wrong, but your approaches are ruling based, right? So you have a cylinder, a cone, a tangent surface, but if you have a sheet of paper and you bend it, the ruling pattern changes all the time. So this is why we recently looked into this quad mesh approach. Maybe you have seen it, this checkerboard approach. And possibly, so actually we did some curved folding also last year in the SIGGRAPH paper. Maybe this would help, but still the inverse problem of designing something by cleverly choosing the curves, I do not know. I can choose the curves and you can more or less interactively fold around, but the inverse problem I think is harder. Yeah? So I'm asking because I was thinking that you will work in this direction and I was not wrong. So there will be some grasshopper component coming out and freely usable, of course, for the community, which is extremely nice. It's always a lot appreciated a lot.
Of course.
So, unfortunately, I still do not see questions around. So say, let me ask all the questions, which makes it difficult. Dogs, do you have questions to the team? Can you help me?
I mean, I think, I'm always looking at it from a sort of making or fabrication perspective. In terms of, and making cones is always difficult. And so since there will be cuts, let's say, do you have sort of design principles in mind as to where those could be located? Or is this going to be a potentially driving parameter for how much of what the cylinder radius is, for example? Like from a making perspective and the location of the cut, do you have any observations or recommendations?
So in our approach, the cone, well, of course, you can create a complete cone, but you can probably, for the physical implementation, we will cut the tip of the cone, apex of the cone, so that it's more like a hole there.
So like the example that you have at the end of the presentation.
Rupert, do you have any comments about fabrication?
Yes. Well, I think for the cuts along a cylinder, I guess you can freely choose. I would really say that it would make sense to align them in a way that the fabrication gets easier. So at least for the last model, we built it in paper as well, and it was very difficult to align the cuts so you have at least one continuous sheet with cuts from the side, so it's fabricable or foldable in that way. I also think I would try to make this whole, not only from a designerly perspective, but with any material I worked, like the apex of a cone is, as you probably know, the weak point of the thing. It's a disaster. And also, I mean, depending on the E module of the material, I guess the cone is probably not the best way to do it, but I guess our method, what I really like on it is that you have something like a low poly modeling approach that you really can very quickly adjust, and it keeps the boundary. So in some sort, I would say, from a fabrication perspective, what I really learned is put the cut into a planar surface, so there's no bending moment that it has to transfer it. So that is something I learned from things, but there's no special algorithm that we had yet running on it.
Okay. Thank you very much. I think this is really important to address fabrication as well. This is an important part of architectural geometry, to also think about how to build this actually. Do you think that you can realize something on a larger scale, and would it make any sense? Yeah, so maybe not this method, but with curved folding, right? Or is it for a more smaller artistic object? So what do you think about that?
I think there is a comfortable, reasonable scale for actually using curve folding. I would like curve folding to be used in active bending manner rather than extreme large scale that needs to be built. Then you really have to build foam work. I think most reasonable way of using curve folding is to leave the material like bendable, maybe using composite material, because there is a nice way to make hinges to composite material, while that generally allows it for large deformation in elastic range.
Okay, thank you. I think we should probably move, unless I see questions, but at least I don't see them. So let us move to the next paper. And I have seen Yuta around. He is also not so Yuta Shimoda and Tomohiro.
So Yuta will be giving the 5 minutes talk.
We'll be giving the presentation. Very good. So the next paper is on flat, foldable, rigid origami with uniform thickness panels. And Yuta I see him around here, but I do not see him on stage.
Yeah, there is a time lag of this YouTube streaming. So
I see. Yeah. No, he's moving to stage even on my screen now. Very good. Yeah. You know, I'm not a gamer, so I'm not really familiar at all with such environments. Oh, Yuta, I can see him. Yeah, great, Yuta, to see you here. So the stage is yours.
Thank you. Can I hear me?
Yes.
Okay. And sorry, this is for the first time on the stage, so just. Sorry, how can I share my screen?
When you go down on the left side,
Mm-hmm.
not the most left, the next one looks like a monitor, right? The screen, and this you touch. And then some window will open, and then if you have both screens with your computer, yeah, we can see something.
I see. Thank you very much.
But you're now you're sharing the.
Okay. So thank you for introducing. I'll start. I'm Yuta Shimoda. I have a master's degree from the University of Tokyo, and I'm a structural engineer in Junsato Structural Engineer's Office. Today, I'd like to talk about flat foldable rigid origami with uniform thickness panels. Rigid origami, which is the origami model composed of rigid panels and hinges, is useful for various engineering purposes. Although origami models are mathematically considered to have a zero-thickness surface, this is no longer true when we apply to physical mechanisms. Adding thickness can alter the kinematics of the rigid origami. Therefore, several approaches are proposed to achieve thick rigid origami. There are two major approaches. We focus on an approach based on the shifting rotation. The structures can fold to a completely flat folded state without any interference. The focus of existing approaches of thick rigid origami was limited to developable origami surfaces, but in this paper, we extending the axis shift approach to non-developable rigid origami. We use a mesh composed of degree 4 vertex with equal opposite sector angles, called discrete both surface. In our method, each panel ends up having a uniform thickness. This is a novel property, and the resulting structures efficiently fold up to completely flat, wherein the total thickness is the sum of the thickness of overlapping panels. Shifted axes change the kinematics of rigid origami, so the method applies to limited types of vertices satisfying conditions between thickness and the sector angles. We consider the family of discrete both surfaces with corrugation. In other words, the mountain and valley creases are alternately repeated. The direct construction of such a rigid origami often requires numerical computation using optimization algorithms. However, in this study, we introduce an alternative approach using an analytical loop condition. With reference past researches, we derived the loop constraint as shown. For each interior face, the sector angles around it satisfy the loop condition. Next, we propose a method to add thickness to these surfaces. Oops, sorry. Yes. For thickness accommodation based on the axis shift method, kinematics changes at saddle-like vertex. An opposite pair of axes with mountain creases shift inward, and the other opposite pair with valley creases shift outward. This forms a spatial forward linkage, which is not generally a mechanism. Bennett linkage is the only known spatial forward linkage. We can construct the Bennett linkage in our case by carefully choosing the thickness and the angles. Therefore, we obtain the constraints as shown. We set the design parameters as the sector angles at each corner and the thickness of panels. Now necessary and sufficient conditions for rigidly foldable structure can be obtained. The DOF of design, the number of independent parameters we can choose, can vary based on the numbers of panels and sub-like vertices. We show you a variation of the form and its DO wave of design. And we consider the DO wave of design of the mesh with M and M by N quadrangle panels. DO wave of design of each type is shown in the bottom. We obtain the hyperbolic form. When both M and N increase, the DO wave becomes negative. In other words, the structure is over-constrained. Therefore, for a larger N and M, it is reasonable to find the design method assuming symmetry to make the constraints degenerate. We propose two design methods using symmetry. One is a simple design approach to create a cylindrical bolt shape from a given arbitrary section polyline. And the second example is a design approach using the mirror symmetry about two perpendicular panels. We can construct a bidirectionally flat foldable dome with 6 by 6 panels. And the resulting structure has an advantage for architectural fabrication, like this. Sorry. That's all. Thank you.
Thank you very much. Thank you. Any questions from the audience to the authors?
Yeah, here is the model.
Very good. Yeah, this is good if you show.
Yeah. This is very thick model, and the panels is 3 by 3. Yeah, so this is the first surface, and this is thickness.
Wow. Yeah. Aha, very good.
Yeah, bidirectionally flat for the surface.
This is transformable design. Sure. Very nice. Yeah, thank you for showing these models. I still do not see any questions, so let me get started. You talk here about discrete Foss surfaces. So for me, a Foss surface is a surface with a conjugate net of geodesics, which is a smooth surface. And it is known, as you correctly state, that you have this angle condition for a discrete version. But I think the corrugated versions you show are not really discretizations of Foss surfaces. They are totally different shapes. You just take a discretization constraint from the smooth setting and transfer it to your setting. So is this right, or do I see this totally wrong? So it is not a Foss surface. So you do not approximate the shape of a Foss surface. Is this true? Am I wrong?
I see.
But Tomohiro, do you know what I mean?
So
anyway, yeah, so I'm not sure. So I think one has to be extremely careful with these discretizations. If you take something from the smooth setting, like a Foss surface, and you discretize it, you get out something. But what you get out is a condition. And if you then apply it to a corrugated scenario, which you do, it is no longer an approximation of a smooth Foss surface, but it is something totally different.
That's
so
right.
It's right. Yeah, yeah.
Right.
So my question actually is, what does it approximate? Do you have some insight?
Insight.
I see. So the corrugated version could approximate probably more than what the discrete Foss, like the Foss surface, can form.
Maybe, yeah.
Yeah, with this corrugation. Yeah. So yeah, exactly right. That we are extracting only the condition, like the these opposite angle
condition, yeah,
and planarity. That is the discrete interpretation of these conjugate net. But yeah, that's Yeah, that's an interesting question. Whether like this egg box type, for example, the corrugated in both directions,
Right.
and what are the variations that you can get? Seemingly, it's easier to design globally convex surface, like the positive curve with positive Gaussian curvature than the negative Gaussian curvature. Although you can do the negative Gaussian curvature with these surfaces, but with the egg box, it's a bit easier to make that. So there seems to be some like designer surfaces that can be achieved.
And since you are so active in the area, I ask you another question where I have absolutely no answer yet, but I'm interested in how to do it. So the question is something more general than the Voss surface. The Voss surface, or the discrete Voss surface in the original sense, is you would call it flat foldable, right? No, it's not flat foldable. It is a flexible quadrilateral mesh. I put it like this. So the faces are flat, they are rigid, and they are along the edges joined by hinges. And the question is, do you have any results on how to get the most general surfaces which are built from such elements? So the question, you have an example here. This is clear, right? So this is a
yes, just
very nice
example.
And yeah. I failed to get the solution for that. I have some special cases I know.
Generalization of this kind of surface. Very difficult.
No, if you don't know, it's not a shame. I know nothing, right?
So
it's just I want to. You are so famous for this work, this Japanese group, that I have to ask these questions, to learn something.
So I think so. So it's a mesh composed of quad panels, and then finding a rigidly foldable family of these quad mesh.
Yes.
So that one requires over constraints, so like degeneracy of constraints. So they need to have some extrinsic or intrinsic symmetry. So what we are doing is to luckily find some of the families that have the varieties forms. But recently, I have seen works by Ziwan He. He's from Cambridge. He found some of the new families of these, and it seems to be larger than these flat foldable type, like with these opposite supplementary angles or opposite the angle with the opposite. The same angle constraint. So yeah, it's a study relate. These constraints boil down to the polynomial equations or rational equations. So you can apply. In theory, you can. It's a solution space of such system is the variety of polynomials with these, but with real numbers. So although it's extremely computationally expensive, but there could be a way to complete the list of possible flexible ones.
So there was some progress a few years ago by Ivan Izmestiev. So he classified all 3x3 configurations, so 9 quads in a 3x3 arrangement. And he did exactly what Tomohiro now said. Yeah, it results in some algebraic problem, and he classified all that. But this does not yet allow you really to design something nice out of it. You have some constraints, and this is very far from a design environment which comes close to what you guys are doing. Yeah. And I think, do you need this corrugation? So can you imagine something from thick elements to return to your actual problem? These are thick elements, right? So plates. Could you design something from plates that flexibly moves and does not have a corrugated shape? So without corrugation, this is my question. So if I give you a phosnet, a discrete phosnet in the original sense, is it just in principle not working, or yeah?
Well, it should work. But
should work, right?
Not flat foldable.
No, not flat. So this will not be flat.
Right. So it
will be transformable.
Rolls up to some state and then starts to collide each other.
Of course, yeah. Sure.
But
so
it's
like a Hoverman sphere is also not flat foldable, right? So, but it is a nice design which moves around and creates an interesting effect, and it may create an even more interesting effect if you have such.
There is a work by SOM, from SOM, where
SOM I know, yeah, they built a FOSS surface actually. Yeah, you are right. Yes, you're totally right. This is from Baker's group at SOM, right? Yeah, exactly. Yeah. Okay, so still no questions.
There is actually a question on the left on the YouTube channel.
This channel I do not have. Can you read it, Tomohiro? I do not see it, unfortunately.
Okay, this is beautiful work and very nice presentation. Thank you. Could you comment further on the application of this research? For example, you mentioned an architectural application in which the structure is constructed off-site and then deployed. Does the VOF approach also give you instructions for a minimal set of additional supports or braces that will guarantee the structure will not collapse while in use? What are the other potential physical applications of this research? That's from Elisa Ross.
So, yeah.
Sorry, use brace?
So it's about like how it's applied, right? Well, definitely the 1 degree of freedomness of this structure helps to deploy, and it stays safe once you fix some part of the structure. So I think at the construction site you would like to fix some of the parts of the structure so that that is probably the monotonically changing its length or angled or something. Then and then that you can use it for the control of motion, probably.
Okay, thank you. Where did you see these questions? I did not see them.
It's in the original, like the video, not at the YouTube live.
Maybe I did not open. Yeah, sorry.
I found it.
Okay. Any other questions? Because I
there
think
is another one.
Yes, please read. Unfortunately, I do not see it.
So the question is about for discrete both surface, should every vertex satisfy the valence of 4? Can this technique method be applied to different kinds of origami structures? For next question is the in section 5.1, does the input only contain an arbitrary polyline and universal offset distance for every section? Can there be more freedom in designing the other direction? Well, for the first one, it's the valence of the vertex needs to be 4. So that's exactly what it is said. For the design problem, is it about, so it's using the section curve and then the other direction?
Yes. 5.1 is the generating from polyline.
So are there still more degrees of freedom? So maybe, so one of the things the question they probably ask is whether it's possible to rotate this section instead of just going in one direction.
A little difficult because the opposite angle should be equal. So it sorry. Is it possible? No. I forget. I once think about that.
Okay.
Yeah, I think there was no obvious way to do it. It will break the symmetry that we rely on when you try to have sections that are not parallel to each other. So yeah, probably we cannot rely on this symmetry, but needs to find another type of symmetry to do it.
Yeah.
Okay, so maybe thank you very much, and let's move on to Dux, and he's talking about curve crease paper folding structures and their tectonics. And maybe Dux, you can first say a little bit about your work, if you like, present it briefly, and then we are entering the discussion.
Okay. Let me share my screen. Can you just confirm that you see?
We see.
Can you see that?
Thank you.
Okay. So yeah, so what we're trying to do, I teach at Pratt in Brooklyn, and what we're trying to do is to see how curved creases can be realized at a larger scale. And so what I'm presenting here is essentially a summary of about 3 years of work. We had a grant and we're able to build things with students. This is done in the context of an undergraduate program. So these are still very young students who are, let's say, exploring this type of geometry together with me. And the question was, let's say, which kind of curved crease paper foldings can we realize as sheet structures with compliant hinges? And I'll show examples of what that looks like. And we're trying to sort of realize proof of concept ideas. So these are not meant to be, structures that are much larger than a pavilion, but still, in scaling these things up, we learn a lot about how to put these things together. And one goal in this way of working is to essentially find workflows that are reasonable. So first, I mean, in this group, this is very obvious, but for the audience, there are 4 canonical types of developable surfaces. And if you want to design curved creases, it's actually not so easy to find a method, let's say, that is relatively straightforward. Now, luckily, there is one case which is trivial, essentially, which is the case that we're showing at the bottom here, where you're using a mirror reflection. So you have your, in this case, a general cylinder, you intersect that with a plane, and then you mirror reflect the part that you cut off at the bottom and move it back up. And since you haven't changed the state of the surface, we know that this can be realized. There's, from a design perspective, a benefit that the crease is in a plane, which helps it to find alignment. So this is the sort of summary. We did explorations at a variety of different scales, and with every new studio, I tried to find constraints that sort of address a very specific aspect of making. So, and I will battle through these examples to show you what the individual aspects were that I tried to tease out that are relevant for design. This is the sort of culminating example. We made this little pavilion here and used an architectural reference, which is the Jean Prouvé gas station, to sort of hold on to some basic design principles in architecture, and then realized it in a different way with a different material. So let's say, monocoque constructions, one might argue if this is the right term. I used it because it's, let's say, it's convenient to describe a double shell that is sort of connected at many instances. And one important way of trying to realize that is how can you create a volumetric structure with curved pieces? So that was one aspect that we needed to look at. We needed to be able to turn the corner. In this case, we were interested in a moment connection, so we did some investigations about how that could happen. We then sort of devised the method by which we can fold the outer shell and afterwards the inner shell. So here you see the mirror reflection planes and the sort of resulting surfaces and how we go from a cylinder at the top left to the final design at the bottom right. And let's say in terms of I mean, tectonics is a word in architecture that is useful because it's not very well defined. But if we think of how we want to put things together, then the seam or the joint of parts is important. And the first investigation here was, well, why don't we try to simply put that into a plane? And I was interested in challenging that in the later results. This component on the right here is pretty large. It's 3.5 meters. This is realized with vulcanized paper. I can get into the details if there's interest about what this material can do. These were smaller studies that had to do with hiding structural parts within. So on the bottom right, you see sort of a triangular box plate assembly that is holding the spool together. It yielded some, let's say, structurally satisfying examples, but we thought that we could go further in challenging that and figuring out how to make all surfaces structural. In this design here, the investigation was how could lapped joints create a larger object. So if you look at the bottom right, you will see how parallel surfaces can be used for rivets or other adhesives to bring components together. And here we have a connection type of the final design. So on the top right, you see the component with the moment connection. And let's say the specific topic for this investigation was, can the seam between components also be made with curved creases? So the mock-up, the prototype at the bottom here, at the left is closed. And in the middle, you can see how the two components are separated. So there's a, let's say, 15-centimeter gap in this case. And the building seam, the joint between these two parts, is also using the same cylinders and curved creases, which allows for sort of interlocking of parts and if you wish, self-alignment or automatic alignment. When you're pushing these things together, it sort of finds the right location where it needs to be, which is important in terms of tolerances. And the other constraint that we imposed was that we can only use fasteners that are attaching surfaces, congruent surfaces to one another. And the bottom right is a bottom view of this roof detail. Overall, in terms of the sort of larger assembly, we used stepped joints. So you can see larger bolted connections within. And again, here, the ambition is to find the guide. So there's only, let's say, there's one way that these things can come together, and the bolts are being used to sort of make the precision of the assembly by having these stepped joints. This was an earlier example where we tried to fold the whole sheet. We did some studies on compliant hinges, so that just means that the material is crossing the crease, and we were successful in testing different types of perforations. What is interesting is that different folding angles will require different types of details. So if you look at the bottom left here, you'll see that the dashes are longer and shorter. This is related to the folding angle. because you want to have a subtle way of bending it. So you need to take a material away in some cases. On the bottom right are surface connections where you want to have common tangents. Degree 4 vertices are a challenge to make. So this was a study how that could be realized and how we can keep plates in their position. So these are not really ribs in the sort of primary structure sense, but they are, if you wish, folding guides and make sure that that surfaces remain in the right place in the three-dimensional configuration. Here, this is just to show that the majority of the sheets on the left, those are the ones of the two shells that are coming together, and the parts on the right are these stiffening elements, which were all CNC cut. Here you see those spacers that are keeping the two surfaces in place, and how they were fastened to the inner surface predominantly. There are no holes on the outer surface because we thought that we only want to have access from the inside in order to have a continuous waterproofable surface on the outside. And yeah, we're essentially hopefully demonstrating that we've developed a way to show how these part-to-whole relationships can be built upon, that we're, let's say, continuing a tradition of sheet construction, if you wish, and also that just at the design level, we've shown that while the method is relatively constrained in terms of the sort of, if you wish, the formal range, that there are, let's say, different types of design examples that one can achieve with this method. And that is it already.
So, Helmut, you are muted.
You are right. Thank you very much. So this is not my only problem. Another one is that I'm not really able to read these comments or questions which come in. So if any one of you reads it, I will later look at what I have to do. So if there is no question coming in at this stage, but I may not be able to see it, let me ask something. You have, Dux, of course, you have an undergraduate class, and I think it is more than enough to have this mirror reflective curved creases around, because everything else will be too complicated. But my question is, do you think it's actually enough to get great designs, or would the more general case help to do, would it really help a lot? Yeah, this is my question.
Sorry, can you
how good is it for your case?
I don't know if it's just me, but the connection is not so great, so I couldn't hear your question.
Does anyone hear? Maybe I should disappear.
Did any of you understand the question?
No, it was the question seems to be. Well, I do have a question if before Helmut returns. Oh, maybe he's back.
I think what he was alluding to was the sort of the very limiting, formal range if you're using cylinder reflections. Like there's really, you're in a, let's say, design solution space that is extremely limited because the curvature doesn't change. And so things, appear to become very monotonous very quickly. I think that was what his question was. And I think one way to, let's say, out of this problem is going to be using the work that Clara alluded to that is in the works in the future, which is if we have the ability to go from a cylinder or an arbitrary surface to other specific surfaces, that if that transition can be made, and it can be with the work that Clara is developing, I think we will be able to design a lot more interesting things. So I would, if that was the question, I would agree that yes, the formal exploration is not, let's say, is not very forgiving. It's a pretty tight design space that one is working in.
So before Helmut comes back, I can ask question. So I have a question about the if you measured, like 3D scanned the built-up model, and if that gives some like errors or like difference from the design versus the physical model.
So we've only 3D scanned things that we made that weren't as predictable as cylinder mirror reflections. I think the biggest deviation, or the problem of deviation, has more to do with the buckling of the surfaces at large scale. So you see artifacts of buckling, and you try to correct that with these inner spacers, because at that scale it is really difficult to expect the material to be in the right position. And I think another problem is the sort of obvious offset that you get when you're lapping materials together. So whenever material accumulation occurs, once that happens twice, your tolerances can be off really quickly. So it's, in our case, easy because the material is so thin, and at that scale, it sort of becomes just part of the assembly tolerance. But you have to be very careful how you lap material together. And let's say one result of this was actually one, if you wish, one constraint that resulted out of this were these stepped joins. So if you want to have things that fit into each other, it becomes difficult to realize that in a building assembly where one part needs to fit into the next and fit into the next, because you start to move away from your ideal geometry too far, because you're offsetting material with every additional offset. But if your question is, have we 3D scanned this and checked how close it is to the idealized or correct geometrical model, we've not done that for these examples.
That would be fun.
Yeah. Oh, definitely.
Is there a planar part in the planar patch inside this cylinder, or is every part of the surface is curved?
The only planar parts are these sort of the end caps where the two bays are coming together. Everything inside is curved.
Can you hear me?
Oh, now I hear you.
I lost the connection somewhere. I told you I'm not familiar with such things, and the camera doesn't work anymore. So that's, as expected, somehow it went reasonably well for some time. But I could see that you have a good conversation, but I could not join. So is there anything else? Any questions? Or
I would have a question concerning the cylindrical surfaces. So you have cylinders with equal radii, so you can join them to build, I'm not sure if it's a sandwich or whatever we call it. So this double layer thing, is that one reason for it? So trying to have similar radii, or is it, I guess from that perspective, how did you design like the sandwich? Is there like a distance in between curved folds that must be respected, so it stays curved, so you have more control on the geometry? Or was it more really design freedom and then try to touch it sometimes in between?
So in the phase of experimentation, there were moments where the surfaces were intersecting, for example. And we tried to turn these into building joints, but because you have, let's say, you have building elements coming together now along a curve in space, you don't really have a surface. And so that turns into a weak connection. So we tried to avoid that by, yes, pulling the two shells apart from each other as far as possible and using the intersections for the joint. And relative to your question about the cylinder, we used Elastica curves, for the original cylinders, because those are obviously conducive. So I would say, yes, in this last case, we tried to keep the surfaces apart from each other as far as possible in order to accommodate connections between building elements.
Did you try, because you said the deviation of the material thickness played a big role. Did you try to adapt the geometric model? Or, I mean, yes, with bachelor students, it might be difficult. So you have at least partly a partly adaptation to the material thickness, or is it just like the original 3D model is just surfaces without any thickness, so zero thickness surfaces, and then just generate the pattern from that?
So let's say the guiding principle was the geometrical surface was in the center of the main sheet, and we only allowed lapped conditions 2 times in either direction. So that was how we controlled it. There's a question here: can it generate more complex topology, like with some holes inside? So I think, if I understand the question correctly, so the only holes that we can create are really holes in, let's say, within the surface. You can, of course, take out entire chunks, but I don't think that would have an impact on the topology, because the continuity is only within the surface and doesn't really change when you cut larger holes in the surface. Do we have another question here? Oh, which other materials would be suitable? Yeah, so this material is not waterproof, and I would say the next steps are to try to realize this in polypropylene. We've done some tests with that already. Metal sandwich panels, like here, there's a product called Alucobond, can be useful for this endeavor, and then of course sheet metal. So yes, this should be realizable in metal.
Okay.
Are you interested in working with fiber reinforced plastic?
I have used composites. The problem is that the let's say compliant hinges are not so trivial to achieve.
Right.
With composites. But yes, can obviously be done. I think we're over by 5 minutes.
Yeah. I think we should end. That's about the time expected. Okay, on behalf of Helmut, thank you very much.
I guess see you later.
Yeah, thank you very much for joining this session.
Thank you.
So we'll see. The next session will be in 1 hour, right? The plenary session. Good. Okay, see you.
Okay, see you later.
Hi.
Hi everybody.
Hi.
So,
just in time.
Hello again. I'm hoping that Alex will come in so he can do his presentation. If not, I've got it here.
Just to make sure it was working, I started the YouTube live, so you're on YouTube right now. Just
okay.
So you know.
Hi world.
Hello world.
So, hello Alex. Is that AS must be you, but we can't see you.
Yeah, the camera doesn't work on this computer, but hopefully it won't crash as much as the other computer did this morning.
Okay. Can you share your screen still though?
Yeah, everything else works.
Okay. So we're waiting for Laurent.
He's coming.
He's coming.
Oh, there he is. I can see him. Yes.
He's on.
Okay.
Hello, Laurent.
Ah. They are the same as this morning.
Yes.
How are you? Fine?
Fine, yes.
Yes. What we should do? Redo a little presentation or what? Like this morning? Very short one?
I guess so. I imagine the audience is different from...
For this morning? Okay.
Morning. They wouldn't have come twice.
How many people are there then? Is it only the people in the room we see, or also people that just see the link, the YouTube link? I don't know.
Some people are only on YouTube.
And I think for the European audience, maybe they follow the sequence. So they go to room A for now. So it's more for American time zone.
Uh-huh.
Okay.
Yeah.
Okay, who begin? Some very short presentation now. Eike, you would begin?
Eike, your microphone's off, but I think he doesn't even present.
Yeah, I'm going to leave the stage. I think I'm confusing you. I'm second author. I just wanted to hang out here.
Okay.
Jonas is going to present.
Yeah.
Okay, Jonas.
That's me. But I work with Eike together for several years now. So we're doing topics together, and maybe this leads to some confusion. Okay, I will share my screen, but I will not go full screen as this caused some problems before. Okay. Do you see my presentation?
Yes.
Okay, so welcome to my short presentation on kinetics and design of semi-compliant mechanisms. We are me, Jonas Schickere, and Eike Schling, Anna Maria Bauer, and Thomas Oberbichler, who were working on these kinetics, these semi-compliant mechanisms. We are in a field of compliant mechanisms, which are mostly found on small objects. They're quite common because we don't need hinges, but we can create mechanisms that take usage of the elastic deformability. And so the aim is to have a controlled deformation and to use it for large deformations. There are also in the field of differential geometry some findings where it was aimed really on grid structures and how they could deform. So this is also a mathematical topic for differential geometry. And we are also next to kind of bending active structures or kinetic structures even in architecture. So these are transformable structures that take also usage of also use elastic deformation of the material to create large deformations, and some developments. This can be also used to create grid shells. You all know Multihalle Mannheim, or more recent developments, the geodesic grid shells or asymptotic grid shells, developed by colleagues of me and also with me. In our research, we try to classify some mechanisms based on doubly ruled geodesic and asymptotic networks, so all quadrilateral networks, and we choose open and rotational surfaces to have, because they show specific behaviors, and so this is kind of a good classification to because they have similar behaviors within. There's a short animation where you see some grids, how they deform, and actually we're using specific profiles for each type, and these profiles only allow elastic deformation or bending in specific directions. For example, the double ruled only allows torsion, the geodesic torsion and uniaxial bending, so as the asymptotic, but in another direction, in a normal or a geodesic direction, respectively. And so we have some stiffness in the grid. Those profiles the grids are made of are not completely flexible. They have stiffness, and this gives a good quality to the mechanisms, because they are you can create nearly a 1 degree degree of freedom mechanism, not completely, but nearly, and you have some stiffness within the system, which is quite useful for engineering and for real applications. To do some engineering, I use the curvature square analysis. So that means that through all stages of the grid, I record the curvature square, which is a value that I can just multiply with the stiffness parameter of the beam, and then I get the internal energy. So this is actually kind of a fingerprint of each mechanism that shows me how it behaves, or how the internal energy behaves throughout all those stages. So I can record this, and I know a lot more about this mechanism. And we use those mechanisms for some asymptotic examples. You see here the inside-out pavilion, or on the right side the canopy from the Hotel Intergroup, where we also experienced first that this follows really a nice mechanism in the meaning that the transformation follows a specific shape, and you cannot push in any shape. It is really quite under control. We did some research designs on that, and it's just an example from Frederick Houston. So some architectural application. This could be a roof structure which is transformable. So the goal was here to have not a static solution, but a more transformable solution. So you can deploy and pull back or whatever. At the moment, we are working at the kinetic umbrella, which is a transformable grid structure made of glass fiber reinforced plastic lamellas. And the structure can open up to a radius of 8 meters. And there should be some shading elements, and we want to build this in summer. And actually, we have started to order the stuff and go into the building construction phase next month, probably. So we also did this analysis of curvature square and internal energy states here too, to identify whether how we need to actuate the system. So do we need to pull it down, or do we need to push it up? You don't know that just from geometry. We need to have some insight into the energy states and into the minimum energy states to know what's happening, and also to choose a correct profile or a good profile. the material just seems to be very suitable for this application because it allows large deformations within the material. And here you see some detailing, and in the middle an actuation system. For example, you can put a cable around and you could like tie it together. Which you can calculate how much force is needed for that. But this is just one example. So this whole structure will serve as a testing field to try different actuation systems to test them. Okay, actually, I'm done with that. I have a couple of models that I could show, but I don't know what's the procedure now. Do we have questions or discussion now, or maybe presentations first? I don't know.
Or maybe some question. If someone has some question on this, on your presentation.
Maybe before that, I can show something because it was just arrived. Maybe also for you, Ike, very interesting. Just 1 hour ago is the aluminium parts for the node detail. They are just here now. So this is the detail for the umbrella structure. It actually looks quite beautiful, and it fits. it's rotating, so trying to get rid of friction. It's rotating, and very happy now we can order this piece.
Is rotating to figure the rotation of the tangent plane along asymptotic line?
Yeah, this is actually in the whole structure. So the rotation axis always stays normal to the surface, and this is actually this hinge in here. So the lamellas here, which are just very short pieces here, are the asymptotic the lamellas, and they will stay asymptotic lines more or less. Yeah. Or was this the question? I don't know. What did I answer your question, or I don't know?
Yeah. I have some question for your construction. You need some net without singularity.
Again,
or you can manage some singularity. Can you manage some singularity in your net?
Singularity?
Yes, singularity is where the several asymptotic line comes together, or several.
Yeah, we're not. I have not. This is actually also something we wanted to do. Ike is also very interested in that. And do we find mechanisms on singularities? I think we assume that they more stiffen the whole structure more. So we did no tests on that, and no simulations on grids with singularities. But we're just starting with this actually. So.
But actually, the very first time we noticed that there is this mechanism in asymptotic nets was actually in our prototype. That was in 2017. It was a steel prototype with a singularity in the middle, based on a Schwarz-D surface. And there we noticed that the singularity in the middle would remain, and the farther you got away from the singularity, the more movement you would get.
That's what I say. But I mean, the singularity itself is then not something that transforms really. It is more a part that stays the same, and other fields where there's no singularity are transforming. So we assume that they are more actually stiffening to the structure.
Yeah, behind you, Eike, maybe you have such thing behind you.
Yeah, no, I was when you just asked, I was thinking, but
no, the other side you have the same model, like nearly the same. The umbrella model.
Yeah, sure. I have the same model here, but that's not what we need now, right? No, but we're talking about one with a singularity, and I don't have a model with a singularity with me now. No.
Okay.
If that's the question. Only our first pavilion, in Munich, the Inside Out, and that had two singularities, one here and one here. But there we didn't test the mechanism because we we constructed this out so that the singularity was never part of one piece. So I can't show anything now, I'm sorry.
Okay, but to get your compliant mechanism, you need something without singularity, no?
Well, we can use, for example, a grid which has a singularity and to push it flat. And the singularity is also more or less flat in all states. So it doesn't change, but the other parts then transform. So it is possible, but the singularity itself doesn't transform, but everything around it transforms. So you can have a system or a grid which includes a singularity, and then you can create transformations. It's possible, but the singularity itself is more or less fixed. This is what we experienced so far, but we don't have real specific studies on that.
And the very interesting thing about that was that with the singularity, the minimum energy state was actually not the flat, the planar state, but the curved state. So if for the timber model, it actually popped up by itself. So you have to press it down to be flat, but through its own energy, it would pop up into a curved shape.
The energy is bending energy?
Yeah, I mean, of course, there are more energies that you could take into account, but for these large deformations, the energy is mainly stored in torsional and uniaxial bending energy. So these are the only portions from the internal deformation or the internal strains that we look at. And we can play with these around. So we can play with these two energy portions, and we can control the state also, especially only in the asymptotic grids. We are able to control the minimum energy state through choosing a profile. Because maybe I show my slide again. Mm-hmm. Just a second. Okay. If you see the slide, there are some graphs down here that mean the state of the mechanism. So, for example, the asymptotic. Do you see my mouse also? Yeah. The asymptotic in the asymptotic graph of the curvature square, the torsional curvature square and the bending curvature square run contrary, which means that if I have a large bending stiffness, the structure rather goes into a spatial state. And if I have a large torsional stiffness, the whole structure's energy minimum is rather a flat state where there's no torsion. So I can control this, but this is only possible in the asymptotic grids. Actually, the starting point for this was because we had models, the same model from different materials. The one was from timber and only at a model scale, and the other one was from steel. And the steel one was just very flat, and we could hardly push it into a spatial shape. And the timber one was spatial, and we hardly couldn't push it into a flat state. So this was actually the point where we thought, okay, we really can control the minimum energy state through the profile only. And that's why we had to get some insight into what's really happening here. So we recorded just the geometric part of the energy, just the geometric information, which is the curvature. And we record the curvature square because this is the sum of the curvature squares, so that we can just multiply this with the material and section parameters. So this is just an engineering approach, actually, to make this happen and to understand what's happening inside the structure.
Something I don't understand. Kx square, what is it?
Well,
for the geometry of the curves.
I have the
what is
three curvatures, which is the geodesic torsion, geodesic curvature, and the normal curvature, and then I can just I need to multiply this with the corresponding stiffness parameters from the profile. Well, I mean, I need to multiply the curvature squares.
What is kx square? What is it?
For example, this is the curvature. This is, for example, the twist, per meter. So some angle per meter squared, and the sum over the whole length of the beam.
Yeah. So what's confusing for Laurent is because you're an engineer, you call it X, Y, and Z, like the axis of the profile.
Yeah.
And for Jonas, this X is torsion, Y is the strong axis, and Z is the weak axis. And I think you, Laurent, you would call them geodesic torsion, TG, would be KX.
Okay.
A normal curvature would be KY, and geodesic curvature would be KZ.
Okay,
Yeah.
I see.
Yeah, there's two options of expressing this, and you always have to choose because we are somewhere in between now, from the mechanical part and the geometric part. And for this formula or function for the internal energy, I choose the more mechanical engineering description.
Okay, thank you very much. Someone has some question in the room?
Do we see the chat from the room? Because I cannot see if they would ask something in the chat.
Yeah, or someone can come on the podium, speak with us.
Somebody's coming.
Yeah, somebody's coming. No, not coming.
Don't be shy.
Okay, but I can show you something that the last time the time was over, but I just wanted to show you the profile from the real structure. Maybe this is a bit interesting. And it's a 8 millimeter times 80 millimeter beam, which is actually quite stiff when you have this in your hands. And it's really, you can't imagine, but you have to, at the end, we want to have this element or this profile to bend this structure. And you can also try other profiles. For example, this one I showed in the session before, which is a slotted hollow section. And this is how you can modify the stiffness parameters, especially the torsional and the bending stiffness relation. So you can have something which is very soft on torsion, then it rather pops into a spatial shape, or you can have something that's very stiff on torsion. For example, a hollow section like this would be very stiff on torsion. Doesn't like torsion, it would like to be more in a flat state. So this is our idea how to control them.
Okay. Maybe we will pass to the next paper.
Thank you very much.
On discretized area stress functions and body force.
Okay. Hello, I'm going to share my screen. Okay. Are you seeing my screen now? And can you hear me clearly?
Yeah.
Okay. My name is Yuzhou Zhang, a PhD candidate at TU Delft, and here also next by me is Pim Buske-Molen, the co-author, and the third author, Andrew Bohart, is not here with us today. Sorry about that. And to talk about a bit about the area stress function is a nice way to describe the stress in 2D structure. But here we draw it as a 3D surface just for visualization. The third dimension F here is a virtual one. So, and what's interesting is that the curvature of this virtual surface in the 3D space is the physical stress in the 2D domain. And when this kind of surface is discretized into polyhedral or principal meshes, all the curvature condense as dihedral angles at the crease or the edges here. And correspondingly, the stress also concentrate as forces at the bars between the voids. And this kind of polyhedral formulation is quite nice to describe the structure interact with the contact forces. But it's not clear yet how to implement the body forces. By body forces, I mean the forces directly acting within the domain, but not on the boundary. And to investigate how to do so, we get one more closer look about the formulation of the conventional way. The curvature directly equals to the stress, but has a 90-degree rotation. So the stress in y direction is the stress, it is the curvature in x direction, and vice versa. And here we have a singly curved stress function, so we have a singly stressed object. And if we're going to include the body forces, the stress is not directly 100% the curvature, but the curvature minus the integral of body forces. In here, we have a vertical body forces, and so the constant body forces, so the integral of it is linear. And here we have a hydrostatic stress configuration that have the compression linearly proportional to the depth. And we believe going to develop a way to discretize them. And then we first try to split them into two cases. One only has a horizontal stress, and the other one has only the vertical stress. So for the horizontal stress, there's no body force. Anything can happen as the usual, all the planar phases. But for the vertical one, we do have the integral of body forces we discretize into a stepwise function. And in order to keep the stress as zero in the result, the curvature of the stress function has to be equal to the stepwise function. So we got to this kind of corrugated shape. And the corrugation has some vertical jump, or some jumps which is related to the bending moment of the beam. So if we put the bending moment and the horizontal truss back together, it forms an arches. And the arch in a lower position has the stronger thrust, so the rises go smaller. So this kind of structure, we didn't invent it, we just used the knowledge in discrete differential geometry to figure out, okay, how to actually discretize the stress function and to get a resulting structure. Here I'm going to show you one more example, is area stress function for simply support beam. And this area stress function can be interpreted in two ways. The first way is that all the external forces are acting at the top edge, so we can discretize it into planar faces as usual. In this case, it's a circular mesh, so we're showing the principal curvature here. And the same stress function can interpret another way, that there's no external forces at the top and only has the body forces in the middle. So part of the panels had certain curvature. And we can draw the pipelines, to draw some pipe according to the Chris angle to highlight the stress or highlight the force. And to conclude, the conclusion is that we have developed a way to incorporate body forces in the discretization of area stress function. And one discretized area stress function can contain the information from three functions: the integral of body forces in the two directions, and also the smooth area stress function. And we feel like this discretization is a nice tool to visualize the stress and also the interplay between the internal forces and the body forces and the external load. But whether or not this is helping the designer or the student to perceive this information is still unknown, and can be some work need to be done, and also apply this kind of discretization to a more complicated examples or real life examples would be also interesting. And if I haven't got a chance to try the full screen to show you some animation. So I hope you can also still see is when it rotates, the crease angles become more clearly visible in this case, and also here. Okay. So maybe I should stop sharing now. Is everything went well this time?
Okay, thank you. Hello, Chris. This morning, Chris Williams was explaining us with some crispy ships, some Aries functions.
Yes.
Would you like to explain again, Chris?
Oh, okay. I'll have to see if I can find the image.
Maybe to interplay with Too Young.
Yes. So, well, as you know, you use the area stress function along with Pusha's equation to consider equilibrium in the third direction.
Yes.
Exactly that sort of thing. Here we are. When you have negative Gaussian curvature, then the forces tend to concentrate along the asymptotic directions. And with the Pringle, or the high power, with 4 point loads, then you get concentrated tensions and compressions running along the asymptotic directions. That's probably enough on that. Although we could, what's interesting is that when you look at the asymptotic directions on plan, then they form a grid of diamond shapes. But when you look at the asymptotic directions on elevation, then they form triangles. And these triangles act like cantilevers.
Yes. And is the question to me? so if I'm going to jump in.
Do you have your, can you share your screen, Chris?
I can.
But I also can share figures that I work in the noon. I'm thinking, okay, it's a nice questions. And let me do that. Okay, can you see a figure now?
Yes.
Yes, that's my interpretation of the Pringle. So I discretize into 4 triangles. So in the upper part, and the middle is the vertical projection to the flat ground, that some members are compression and some members are in tensions. And the bottom one is the pyramid shape of stress function. So that's my understanding that more or less this should be echoing what happened in the Pringles. And in this case, like, we do have constant tension and constant, more or less constant tension and constant compression along the symptotic and the principal curvature. So I'm not sure if this is helping.
Shall I share my screen?
Sure. Maybe I should stop first.
Maybe. Yes, can you see this is a very bad diagram, very rough sketch. What happens is that here in plan you have the Pringle, and this diamond shape is formed by the asymptotic directions. Then if you have a little patch load here, you've got 4 of them, 2 downwards and 2 upwards. Then here you've got a little high pass shell like Felix Candela used to build. And you get tensions and compressions along the principal curvature directions carrying the load, and that transfers the load in shear to the asymptotic directions, and you end up with a concentrated tension along the inside lines and compression around the outside, which corresponds to a constant moment in plan. But then in elevation, what happens is that the asymptotic lines form these triangles. This is a very bad drawing. The asymptotic lines form triangles because they appear to be tangential to the top of the curve. And these triangles are like cantilevers, if you like, where these 2 point loads here are supported along the line here. So, but I think it's a nice problem. And as we said this morning, the corresponding stress function looks a bit like this. But it's quite a nice problem because it's actually so simple, but it's still quite confusing. Of course, you can't have these concentrated forces because they correspond to infinite stress, and that will give you infinite strain, and you get very large displacements, and those large displacements cause bending moments, which then cause things to spread out. But if you replace the point loads by patch loads, so it's better to use your fingers to load the Pringle than a biro, then you get a more even distribution of stress. So I hope that answers your question, Laurent. I think you're muted, Laurent. I can't hear you. Laurent, you're muted.
Okay.
Okay, good.
Good. Phi is your Airy function there?
Phi is the Airy stress function, that's right.
Oh, okay. And I would like to ask you, in your discretization, Chuyang, you say that you use a discretization of the Airy function graph over the plane, and in your discretization you looked for a polyhedra surface. I would like to know, looking this Airy graph function like your surface, the curvature of this surface has some mechanical meaning?
So the curvature is the mechanical meaning is the stress directly. So the orientation is the 90-degree differences. So when you're traveling along the one axis, if you experience certain normal curvature, actually it means that you have the stress in the opposite in the 90-degree rotation direction.
Yeah, but in your paper, at some point you say you have some integrals of the second derivative which are still a finite number, but they speak about the slope of the crease.
Yes.
And the angles, the dihedral angle, has some meaning in your model?
So when the curvature is spread out, is a smooth curve. And when the curvature we have a zero curvature on one hand and zero curvature on the other hand, the curvature condenses into the kink angle.
Yes.
And the concentrate kink angle is the concentrate, or we can use dihedral angle to describe it. And it becomes an angle of crease. And in the structural sense, it's become the stress to be concentrated as forces at the edge this is a continuous surface.
Yes, but these angles.
If you have to measure in this direction. So if this is 0 angle and this is maybe 10 or 15 degrees, but in the isotropic geometry, we describe as the differences of slope. So if the slope is flat and this has certain maybe 1 to 10th slope, so the angle is the slope differences.
But after that, you look for your Airy function and you reconsider as a discretization some isothermic discrete parameter. And in some sense, you have this surface, which is a graph like Airy function, and you look reparameterize this surface like with isothermal parameter. This has some meaning.
So in purely geometry way, maybe it's more natural to discretize the panels into flat surfaces. But in the mechanical way, like we also have to consider the integral of body forces. So the curvature of the panels, if it cancel out the integral of body forces, like the result is zero stress at the patches. So in my paper, I propose to occasionally using the curved panels, and the curvature of the panels is 100% controlled by the integral of body forces, to result in have the zero stress in the void area, and all the curvature, all the stress is only concentrated on the edges.
Yes, but why the quad mesh that you are using, you need that it gets on inscribed circles inside?
The inscribed circle is meant to derive the principal stress, and the principal meshes, if the flat the planar principal mesh is to describing the principal to approximate the principal curvature in conventional discrete differential geometry. And in here, if we also still use this technique to describe the principal stress, the panel should be curved, but it's still better to have the
Okay.
Hello, sorry, my internet might not be too stable for today.
Yeah.
Okay. If I go back to a few words. So in the circular meshes, it's still good to have the principal curvature. But in here, we want to show the principal stress. And even though the curved panels, we propose using curved panels instead of flat planar one, but the curved panel should still have these kinds of concyclic conditions to reveal the principal stress law. And yes.
Okay.
So it's using to extend the definition of principal mesh and to craft it in a way to visualize the principal stress.
Okay, good. Some question in the room? Ah. Okay. Chris, you want to present your paper?
No, I can go, Chris.
Yes.
You just won't see my face.
No.
So our paper is tension principal curvature cable nets on minimal surfaces. And we're interested in that not only because you can create tensile structures out of them, but also compressed ones if you just reverse the forces. It's easy to find surfaces which have principal curvature coordinates, which are the red ones in this picture. and you then automatically get the asymptotic directions at 45-degree angle at every point. We can establish the equilibrium equation of a node like this, and using that in a dynamic relaxation solver solves the problem very fast. But our paper is really about the numerics of this. And we can just first observe that regardless if we use principal directions or asymptotic directions, the boundaries must follow asymptotic directions if they are free. We can do a Gauss map of this surface, and we can also do a south pole stereographic projection of the Gauss map, and we can see that the outer boundaries are rather similar for these two different structures, but the direction of the interior grid differs, which is due to their directions. The mathematics side starts with a pair of complex surfaces P and Q, and we apply the Weierstrass NEP parameterization to map from a complex point up to a real point on our minimal surface. When we do that, we don't automatically get the coordinate system to be aligned like we would like them to be, and therefore we also make use of the Gauss map, because we know that P and Q will share the same normal on the Gauss map, and after some elaborations, we can find this expression that links the normal to the coordinates of the principal curvature mesh. This leads to, we can also establish a net on the unit sphere, which is in static equilibrium with one set of members in compression and the other in tension. It's given by this function, where we apply equal and opposite wrenches on two points on the sphere, and they don't necessarily have to be on the poles of the sphere. The forces in these members are inversely proportional to their lengths, whereas when you map this Gauss map to a minimal surface, the force in the members are directly proportional to their length. And by varying alpha and beta, you can get the very well-known catenoid and helicoid. We've also tried to do this on the Friotto eye, this iconic shape on Friotto's minimal surfaces. You can do it with a soap film model, and here's a numerical model trying to model the same thing. And we can compare this geographic projection of the Gauss map of this surface, and then we have tried to construct the same analytically. But we haven't really got the same match yet when you compare the two of them. This point corresponds to this point on the curve. So this kink here is, it's up there. We've already talked about this Pringle thing, which is a property of these surfaces, but it could be interesting to note that in this minimal surface, the asymptotic lines which run from a free edge to the support somewhere down here, they are statically determinate because they only have one load path down to support, whereas all the asymptotic members which cross this line of symmetry, they are statically indeterminate because they have each of their ends down at the support, and there's always two of them crossing one another. Okay, yes. Thanks for listening. And this is a quick and brief overview of our paper.
Thank you, Alexander.
Thanks.
Nice paper.
I've actually got a program which produced the Friotto eye, which I can run for you now, if you like. So can you see my screen? You're still sharing?
Yes.
Yours, Alex.
No, I'm not.
Not? Oh, I still see yours.
But I see your screen when you start sharing.
You see my screen?
Well, not any longer because you're close to share.
Oh, okay. So do you see my...
Now we see your desktop.
You do? Okay. So, so this is the simulation. It's a soap film in a circular boundary, although you can do it in a sphere, which is better because you then get principal curvatures at the edge. If I rotate and zoom, then you can see it better. But the interesting thing is when you move the support up like this,
yeah,
then can you see the lines? Are they clear enough to see?
Yes.
So you can see the red line here is the cable, but you can see there's a very large spacing of the black lines. And that large spacing means that the curvature theoretically becomes zero as you approach the support. But then if you drop the support, if you drop the support, then the spacing here gets bigger, and as you drop it more, then the spacing here is now becoming infinite, corresponding to an infinite curvature at this point. So there is a unique height for the support at which these are the principal curvature lines, at which the principal curvature lines, I should say the cables cross at right angles, or meet at right angles. And when that's so, then you have a finite curvature at the support. So there is, if you like, a special case, a unique case, which is what we would ideally want to model.
Okay.
So it's a unique case. The assumption is that the exterior boundary is at infinity, where it gets close to a catenoid, I think. So there's a nice problem for you to solve, Laurent.
Yeah. What is the variational problem that you use there?
Sorry, what is the?
Yeah, what is you solve this? You have this picture with by variational property.
It's a very simple program. We're basically just solving Laplace's equation. So for all the interior nodes, they just move to be at the average coordinate of the four surrounding nodes.
Yes, is Laplace equation, but which boundary data you put in your?
Oh, right. Well, can you see my screen still?
Yeah, more or less.
Okay. Okay. So.
Okay, good, better.
If I zoom out, oops, I have to pan as well, and then rotate. The exterior boundary is the points affixed to a circle, but ideally that should be as far away as possible. but you can also do it on a sphere, and that's better because then this line becomes a principal curvature line. Where a minimal surface meets the sphere, it meets in a principal curvature direction on the minimal surface. On the cable here, there's a constant tension all the way around the cable because there's no shear stress. So all that we do is just allow the points to slide around the cable, and then we automatically get the principal curvature directions on the minimal surface. You can also do it to get the asymptotic directions if you prefer. But it's very, very simple, the program. And we use Verlet integration, which is very similar to dynamic relaxation for the solution.
Okay.
And Alex has written lots of programs like this. In fact, Alex, you've got a program which runs on the GPU, haven't you?
Yeah, the video of the bridge that I showed solves on the GPU.
Okay. Good. So I don't seem to be able to stop sharing screen. How do I stop sharing my screen?
Okay.
Or I don't know, maybe.
Someone has some question in the room?
Maybe I have one.
Yeah.
Just again on the topic or the statement in your video presentation that did I get this right, that you say that this asymptotic grid shells work without bending and only with axial forces? So this is something we addressed with the chip, the Pringle also before. But can you confirm this now, or is this limited? Make Did you understand?
Yeah, I got your question. We're still trying to figure that out, I would say. We can derive the stress function for patch load and then see how that affects the asymptotic lines that bounce the patch. And that indicates that you will get tension and compression in a pair. But yeah, that's a theoretical solution, I would say. Not sure that if that happens in reality, you will always have. I mean, the area stress function doesn't take material properties and kinematics into consideration when we solve it. So it might be that there are dissipation in the system that introduces other effects than the pure tension and compression pair.
Yeah, of course. I mean, but in theory, you can like find a model where you can transport the forces through actual forces only. This is somehow what I understood from this statement. But you are still working at it there. I'm very because this is a topic I also work with, so I'm of course very interested.
Yeah, we that's our understanding of it at the moment, but yeah, there's still some work to do before we can confirm it. Professor Heyman has a talk in Madrid from 2005 or something that you can find on YouTube, and he talks about the similar things and he expresses it as the force running straight through the surface, and we believe that this is an interpretation of what he's talking about.
Okay.
Could I ask another question? I noticed, by the way, when you're outside and you come in, you miss about 30 seconds. So when you're in the audience, you're 30 seconds delay. So I might have missed the answer just when I came in. But I think what you are talking about, the load bearing of the continuous shell, right? And Jonas, you were asking about a grid shell, and I think there's quite a big difference then. Or did you answer that?
Well, in the continuous version, you would definitely have dissipation along the asymptotic line, so it would spread out. Whereas in the grid shell, you can only have the dissipation occurring at the intersection of the members. So then the stiffness of the member would come into play, I would say, of how much dissipation you would get. I mean, of course, you cannot have one of the members being compressed and stretched depending on the load and have the rest of the grid unaffected because they are attached to one another. So there will be some dissipation of that force, but in theory, that's how we understand that this kind of structure should work.
Mm-hmm.
Yes. Can you hear me?
Yeah, we can hear you.
Yes, it's interesting that the areas away from where the load is are perhaps the most interesting, because what happens is that if you have a point load, then the load has to travel to the ground through an area where there's no load. And if that's the case, then if you have negative Gaussian curvature, then the tension and compression have to go along the asymptotic directions for equilibrium in the normal direction. So to a certain extent, I guess, the asymptotic grid shell behaves like a continuous shell in that case. But of course, you probably don't have the bracing between the panels to give you the shear that you might need under the load itself. I think the loading, the way the shells carry load is very, very complicated, and it's very, very difficult to understand. In particular, how much support a shell needs to carry a certain load, and how much you rely on bending stiffness as opposed to membrane stiffness. I see you've got a picture. Oh, you've got the picture of the Pringle.
Yeah, and well, this is a cut through the Pringle, one can say, and the corresponding stress function. And this small part here is a high part on its own, corresponding to the patch load that acts on the real surface up here.
But there are also how to say, the inverse apex down there. So what would happen there?
Sorry, which? This
so
one?
In the two 90-degree cliff intersect, there's a point you say is a saddle point, and in the bottom there's a very downward valley. The lower point there. Mm-hmm. So what kind of point load is at this precision?
Yeah, corresponding to the force in the asymptotic lines.
Okay.
Yes. So.
Or do you mean the kink here?
I'm more curious about the point down below.
That point?
Yes, but I will think through it. Maybe I have nothing too clearly now.
Okay. Thank you very much. We have to finish our session now. The organizers tell me that we are out of our schedule. Thank you very much, all of you, for this very inspiring discussions and this on the asymptotic link between asymptotic geodesy, asymptotic lines and the mechanics are very promising fields. Then, thank you very much, and see you soon.
Thank you. Thank you.
Thank you.
Thank you.
Get out.
Live streaming is on. Live streaming is on.
Okay, how about now?
Very good.
Very good. Good?
No, you still have this echo.
Still have this echo. Is it like very disturbing? Should I try to...
I think it's fine. I mean, if you mute yourself while we speak, and then I can mute while you speak, then it should be fine.
Okay, okay.
All right, I think we're live, right? Okay, welcome everyone to the second instance of this session. My name is Mark Pauli. I'm chairing the program today. As you've all seen, we had some technical issues throughout the day, but we hope things are stable now and we can have a good session. We might actually, it seems, miss out on Helmut, who had some connection problems, and it's not clear whether he will be able to join us for his presentation. But we do have the second author of the paper, so Eike will tell us about the components of that work, at least that he was working on, and maybe some of the other aspects as well. So we have 3 speakers today, and 3 papers like we had this morning. And let me very quickly go through the different papers. So we have architectural freeform surfaces designed for cost-effective paneling through mold reuse, which will be presented by Davide Pellis. We have form finding with isotropic linear Weingarten surfaces, which will be presented by Xavier Tellier. And we have computational design and optimization of quad meshes based on diagonal meshes, which will be presented maybe by Helmut, if not by Eike. So the procedure we're going to follow is we'll have short summaries of the different papers, and then we'll open the floor for some questions. Then we move on to the second and the third paper, and we can also then at the end have a discussion more globally about all of the aspects. Please, if you have a question, step up to the podium or write them in the YouTube channel chat. And we will monitor that, and I can read out the questions for you. But you're also very welcome to join us on stage. I think it's always nice, to see people directly who are asking questions. But with that, I think we're ready to go. Davide, I would give you the floor for the first paper presentation.
Thanks, Mark. And now I cannot find, I don't know why. Can you? No. Okay, I will share the full screen. Okay, I hope you can see. Okay, so hello everyone. I will do an overview of our work on architectural freeform surfaces designed for cost-effective paneling through mold reuse. And this work is about the smooth panelization of freeform surfaces. And here, the manufacturing of these curved panels requires the costly production of molds. And on a generic freeform surface, one need a different mold for each single panel. And this can lead to cost explosion. And in this work, we want to design surfaces that own some kind of shape repetition, such that this can be cladded with panels that are formed on a reduced number of molds. If panels are rigid after production, one can look for surfaces with extrinsic repetition, and one of the easiest way to get its extrinsic repetition is by designing shapes through symmetries, or to use special surfaces like rotational or helical one. In all these cases, we can get a perfectly smooth panelization by repeating a reduced number of panels. But if we want more design freedom and have some shape repetition, we have to give up a bit on the quality of the resulting panelization and look by allowing these small kinks and gaps between the panels and look for local shape repetition. The local shape of a surface at a point can be described by the two principal curvatures. And if we look to the lines along which one of the two principal curvatures is constant, and the lines along which the other one is constant, we observe that in general these two families of lines intersect each other, meaning that at each point the local shape of the surface is different. But there exists a special class of surfaces where these two families of isolines run parallel to each other, that are called Weingarten surfaces and are characterized by having the two principal curvatures in functional relation. Along these curvature isolines, we can dispose panels that can be formed on the same wall. And in this work, we show how to design Weingarten surfaces that have a fine linear curvature relation between curvatures with a special class of web meshes that are called principal symmetric meshes. And we also show how to design the panelization of these surfaces, and we compare our method with the existing one. Then if panels are realized with flexible materials, and so this can be bent after production, we can look for surfaces with intrinsic repetition. And in this case, we can start from a surface with some kind of extrinsic repetition and apply an isometric deformation. That is a deformation that preserves the lengths and the angles on the surface. And we also show how to easily implement isometric deformation of surfaces directly on quadrilateral meshes. And these are some Weingarten isometric surfaces designed with our procedure. And that's it. Thanks for your attention.
Thank you, Davide, for this summary. I do have a bit of an echo. I don't know where it's coming. Okay, it's good now. So as I said earlier, if you have questions, I'm monitoring the chat. There's nothing there as of now. You can, of course, also come to the stage. But maybe I'll start with one question first. So you mentioned this construction of Weingarten surfaces using principal symmetric meshes. Can you maybe explain a bit more what they are, how it works, and what maybe other uses for this type of representation could be?
Sure.
Are you still okay?
Yeah. Do you hear an echo?
No, it's good. Yes, it's good.
Okay, perfect. So principal symmetric meshes are somehow a discretization of networks of curves that run symmetrically to the principal curve directions. And we work on these meshes motivated mainly by aesthetical reason, because somehow these networks can make more interesting panelizations of some simple shapes. And we found out that these meshes are characterized by having the 5 vertices of a vertex star on that lie on a common sphere. And somehow these spheres represent the Mousnier spheres of the surface at the point, and these carry several curvature information. And then we can use these spheres somehow to prescribe some specific curvature relation. And for example, for Weingarten surfaces, it's sufficient to ask also for constant radii of these spheres at each vertex. And then we also have to ask for constant angles of this discrete curve network. So in this way, we can control also the relation. And for example, we can also design constant mean curvature surfaces and control the mean curvature to the sphere radii. And also somehow these principal symmetric meshes with constant sphere radii, they have constant normal curvature on the surface. So this is interesting also for the design of grid shells, for example, that are realized with congruent circular strips. So every strip is identical, and these are a sort of asymptotic grid shells, a sort of generalization of asymptotic grid shells. And these curvature informations can also be used for curvature adaptive milling. So somehow we can use them to position a tool for milling a surface, for example.
Mm-hmm. And maybe one question which is probably a bit more speculative. We've seen, that you focused on linear Weingarten surfaces, and we will also hear the second talk on linear Weingarten surfaces. Do you have any idea what lies beyond the linear curvature relations? I mean, they could be, of any possible type. These functional relations. Is there anything known? Do you have any insights on this?
Well, this is something that we are working on. So up to now, there are some methods around for the design of linear Weingarten surfaces with principal symmetric meshes. You can design linear surfaces with a linear relation between the principal curvatures, but there are other with the linear relation between the mean and the Gaussian one. And now we are also working on more general Weingarten surfaces. But in this case, much less is known. What we do is, in this case, we do not prescribe any relation, and we try to align the principal curvature, the curvature isolines of Gaussian and mean curvature. So in this way, somehow the relation is emerging spontaneously from the optimization. What we found here somehow is that since this optimization is it's not easy because it involves very high order derivatives. And then we failed with meshes, but we found effective an approach with these spline surfaces. And so in this case, we can control the smoothness of the surface. And somehow we managed to approximate surfaces, but we still don't know exactly what we really can get with general surfaces.
So this is an upcoming paper that you will present this summer, right?
Yes, right.
There's a question in the chat which I think is very relevant. I would like to ask if it's possible to create Weingarten surfaces with Grasshopper. And I think the answer is soon, right?
Maybe soon. This is we are planning it. Yes.
So Davide plans to release his code. And I think it's an important aspect because I think they are a very rich and interesting class of surfaces, and making these type of optimization methods accessible to a broader community, I think will only strengthen the interest to study them more. There's a lot of things that are not yet known, as you mentioned.
Yeah. For now, we are planning to release the Python code that will be anyway quite easy to use. But yeah, why not? Grasshopper tool, why not in the future?
Sounds great. Okay, I think the YouTube video is a little bit behind. I don't know if there's more questions. I don't see any at this point. So I would suggest we move on to the second presentation, and then reserve some time to discuss all three papers together at the end. So the second paper is by Xavier Tellier. Xavier, can you come onto the stage? I don't know if you can hear us. Xavier is moving.
Yeah, so I think they hear us only 30 seconds later in the audience. Right. I realized that before. So when you say it, you have to wait.
Yes, I realized that too.
Live streaming is on.
Okay.
Hello?
Okay.
Great. Is the sound okay this time?
I'll give you the floor. We have echo, but I turn off my mic and you take it away.
Okay.
It's on.
Okay, so let me share my screen. Okay, can you see my screen well and hear me also?
Yes, all well.
Well, good afternoon, everyone. So I'm glad to present you results from my PhD work on isotropic linear Weingarten surfaces. So that's work done with Cyril Dout, Olivier Bavrel, Laurent Wirtz, organizing this conference. So the starting point of this work is on double curvature structures. So we know that these structures may use a very small amount of material, so they have a role to play in reducing the carbon footprints, all the environment footprint of the construction industry that we were discussing earlier during the keynotes. And at the same time, they can offer very expressive shapes. But their main barrier at the moment is the complexity of fabrication and the fact that structural performance is not guaranteed. Some shapes are very effective, some are very bad regarding to mechanics. So the question that we focus on is how to design a curved envelope, accounting at the same time for fabrication, making it simple, cheap to fabricate, and structural efficiency, using resources wisely. And in particular, in this article, we look at the following problem. Let's say we have a target boundary, we have a site that's already defined, we have to fit a grid shell on a target curve. How can we design a grid shell that has at the same time planar quadrangles and such that the beam layout is funicular for a uniform vertical load? So for sake of simplicity, we'll focus only on this the load case, which is really the most important one. And to achieve these goals together, we actually wanting these two properties at the same time, we have quite a highly constrained problem. We ask a lot of properties to the geometry, such that more regular approaches give quite poor results. For example, if you try to start with a mesh that has a fixed topology or fixed pattern and optimize the geometry, or start with a given shape and try to draw lines on it that will give you the properties, well, you will get approximate solution to this problem. And depending on the topology you choose or the shape you choose, this approximation may be quite bad. So we are taking a less constrained approach to this problem. We are generating the shape and the pattern at the same time for a given boundary. So as a shape, we are going to, in the first time, build an highly vine surface. So that's a little nickname we came up for isotropic linear Weingarten surfaces to make them a little bit less scary. And in the second step, we remesh these surfaces following the isotropic principal curvature lines. So this two-step process, it's actually, you could find it in the 2 papers from the last AAG for other types of highly constrained problem. So maybe we'll start by telling you a bit more about this isotropic linear Weingarten surfaces, and especially how they're related to the ones that Davide told you about. He mentioned the general Weingarten surfaces for which you have a certain relation between the mean and the Gaussian curvature that is satisfied everywhere on the surface. So that's a very general property that gives you a lot of freedom. Here, we are looking more specifically at a specific type of relationship. This function f is a linear one. So we are looking at functions for which mean and Gaussian curvature are linearly related. And there's a last tweak. We are not looking at the mean and Gaussian curvature in the usual Euclidean way, but in the ones defined in the setting of isotropic geometry. So you see we have this little I to differentiate them. And so this family of surface is much more constrained than the general Weingarten surfaces, but they will give us more property, and that's why we look at them. And in particular, they have the 2 sets of properties that we discussed. If we apply a uniform vertical load on them, then the principal curvature lines from isotropic geometry will give you, at the same time, planar quadrangles and beams that are funicular for this load case. So that's one solution of this problem. There are more. But that's the one we looked at in this setting. So these highly vine surfaces, you've actually encountered some of them in in your life, all the paraboloids, they have a constant isotropic mean and Gaussian curvature, so they are highly line. This more exotic pelican surface also falls in this category, and so do these functions that are field heights of harmonic functions of the plane. So here we have quite an interesting variety of shapes that are highly fine. So we focused on a more specific and the following problem is how to get this surface from a general boundary curve. Those are just analytical examples. And to build highly fine surfaces on a target boundary, then you have to solve this equation, which is actually a special case of the Monge-Ampère equation. So that's mathematicians and physicians have devoted a lot of work on them because it has a lot of applications in problems like optimal transport or reflector design. And so the medal, Fields Medal 2018 or 19 is devoted to the solutions of this equation. In our case, we have a special case of this equation. So we just developed a simple resolution scheme based on a discrete differential geometry. We use a discrete model on triangular meshes of these quantities proposed by Potman and Liu. And based on this, we can generate by an iterative process these surfaces on a given boundary. And we have a workflow that looks like this. So for a designer, you would input boundary curves. You would then triangulate the domain. So there's a lot of tools available to do this. You would then solve this equation with the iterative solvers. And doing so, you have 2 degrees of freedom to control highly fine surfaces to explore the potential shapes. So you could set, for example, a equal to 1, and then say, okay, I'm going to vary the value of c. Doing so, you would actually modify the average height of your surface. Low C, you get low height. High C, you increase globally the height of the surface. And with the parameter B, what would happen is you would play with the height difference between the mountain tops and the saddle points. You see here, there's a quite high difference between these mountain tops here and the saddle points. As you push the parameter B to the other side of your grasshopper slider, you would get a much more uniform crest line. So you're able to control the shape at a very global level. And in a last step, once you have a shape that you like, you would remesh these surfaces following the isotropic curvature lines. And then you would get the properties we were interested in the first place, these near-planar quadrangles and beams that are aligned with the membrane stresses, such that you have a very low moments in the beam. So to conclude, we think we have here a tool that is particularly suited for conceptual design stages in which you want to explore quite quickly families of candidate shapes and topologies for a grid shell. Because you can just automatically get a family of shapes with like 2 sliders to play on to explore the shapes. And in particular, you see that even on complex shapes, you would have the topology that would appear from the shape and from the boundary automatically, which is a point usually a bit tricky to do to find the right topology for the optimization to work. And what we observed is that this method tends to give quite smooth shapes that are suitable for architectural practice. So I thank you for your attention. I'd be glad to take questions if there is any.
Thank you very much, Xavier. I know that the live video stream is really quite a bit behind ourselves, so okay. I just want to encourage you. It just means we'll get questions potentially 30 seconds later.
Okay.
Then, but that's okay. So please post your questions in the chat or come up to the stage. There's quite a bit of space up here, so don't be shy. But let me maybe start with one question. Just to clarify, I mean, so one of the, I think, nice aspects of your work is that, as you said, you know, you're solving for the geometry, the surface, and the tessellation. And I wasn't quite sure if I understood correctly. So, in order to get the meshing, you use principal directions on a sort of scaled down version right? That is
Yes.
more flat, so that the isotropic and the Euclidean geometry are very similar.
Exactly.
And I was just wondering, like, how do you do this in practice? Like, as you scale your mesh down to become flatter and flatter, these principal directions might also become less and less numerically stable, right? If you would go all the way to flat, of course, it wouldn't work. Where do you, like, how far do you need to go in order to make this work?
Here, like, we went quite empirically for values having slopes lower than what, for example, 5% of slope maximum, to make sure we had like a good agreement between curvatures, the Euclidean and the mean and the isotropic curvatures. But yeah, we didn't quantify much more precisely.
But the reason for this is mainly because you have tools for the Euclidean principal directions.
Yes.
Because
yes,
you could also, in theory, like solve directly for the isotropic principal directions, right?
Yes, this could be solved directly by just integrating the diagonal directions of the Hessian of the height of this surface. So that's totally feasible. It was just given the timeline I had during my PhD, that was quite the faster option was to use new tools. Existing tools that were able to do this integration and to do especially the automatic placements of the singularities and like making sure that the curvature lines are looped and that also optimized for quite a uniform spacing. So that's would be a lot of work to re-implement this tool just for this purpose. So
yeah,
we found that this method was.
So there is a question in the chat from Cameron. When you discretize along principal isotropic curvature lines, some post-optimization is needed to get planar quads. How does this improve upon the methods of Vuga et al.? So I assume he's referring to the...
Yes, with the method of Vuga et al., you might, I think you would expect higher deflections because you are probably quite further away from a given surface with planar quads and which is also funicular. Whereas here, you know from differential geometry that you are already extremely close to a solution. So you would expect very small deformation of this surface, like going from step 3 to step 4. And like optimizing like step 4 for exact planarity, this would give you very, very small deformations.
Yeah, I think the method of Vuga doesn't look for planarity per se, right? They're just computing a funicular surface, if I remember correctly, but I'm not sure.
Oh, I think they had a little options to take into account planarity at the same time.
Oh, okay.
So, but yeah, that might give they start from a reference surface and they optimize for these properties, but this might give quite large deflections, so, depending on your starting surface.
And I think we had this question also this morning from Eike is the question of to what extent these I-Levine surfaces are the only ones that offer funicular and PQ qualities, and you already mentioned they're sort of a subset of a larger family, and I was wondering, can you say anything about what other surfaces are possible? Is that something that is well understood?
The general solutions of this problem. Well, I don't know about theoretical results. Probably if Helmut was still here, he would have something to say about that. But yeah, I'm not aware of more advanced theoretical results, but possible shapes you can get could be constraints here.
Yeah, I think it's interesting. I mean, what you're proposing is, I think, very much in line with a lot of what architectural geometry has been aiming for. That is, studying classes of surfaces that already have favorable properties, so that you're designing in a space that's that gives you, in this case, superior structural performance, but also allows you to do, for example, flat penalizations. So I think that makes a lot of sense to me. I don't know if there's, let me just quickly look at the chat. I don't see another question in the chat.
Where do you see
Then I
that?
would.
Maybe I
Olivier?
can add just an extra comment. The work of Xavier, well, is really wonderful, and it's within a work that we've been doing in the last 7 or 8 years on trying to more on a pre-processing, so finding forms that are naturally buildable rather than doing post-processing, having a shape that's not working well, and trying to do a lot of optimization to fit a mesh that is buildable.
Yeah.
So we had plenty of work on this topic, and the PhD of Xavier was fantastic, and this is only a quarter of his work.
No, I mean, I fully agree with this assessment, right? And the idea of digitally designing an arbitrary shape and then trying to fix it to perform well is, I think, a thing of the past. I think we should build and design with downstream structural and fabrication knowledge already in place. I think that's a very meaningful way to go about these problems.
Yeah, and especially you have to provide a solution in a really short time in order for a designer to generate many solutions. If for one solution he has to do plenty of optimization, then he will not look at the design space completely. And there's a little chance he get a very interesting solution at the end.
Yeah, that's another aspect I think that is interesting, the ability to sort of quickly explore a design space. And I think for many problems, not just this one, it's, I think, interesting to have a sort of maybe almost like a multi-scale approach, something very quick that gives you fast feedback during exploration. And then once you sort of settled upon a specific design, you can also then afford to run more costly optimizations, for example, and then maybe refine your design step by step. But I'm also a big fan of having, sufficiently interactive feedback to be able to do exploration, because without knowing which shapes, are efficient and possible, it's difficult to make certain design decisions. Okay, I don't see any other questions in the chat for now, so I would propose we move on to our next speaker. So I don't see Helmut. I think his connection troubles have persisted. So I would ask Eike to take over.
Yeah, I think the discussion is our paper is fully in line with the discussion we just had, right? And I also agree that very often as architects, sometimes we have a lot of constraints and we can't afford to add additional ones, but very often there's a lot of design freedom. And then I'm personally actually happy for getting some more constraints, such like construction-aware design, right? So Xavier talked about planar quads and then structural performance, and I think we're very similar in this approach. We're talking here now about planar quads, and well, I would say construction-aware design by looking at, for example, torsion-free nodes or these asymptotic networks that we can then construct from straight and flat lamellas. Let me share my screen. I'm not even going to try full screen, but I think this works well as well. So I will present both the mathematical background and the practical implementation, while I really have to say that I'm more the practical person who tries to build these structures in a model and large-scale models. And I was not the author of this geometric implementation, but I'm going to do my best to present it here. So what Helmut and Kai Gui and Zheng found out to optimize these planar quad meshes and also asymptotic nets is an idea of a checkerboard approach. So what we're trying to do with this is we're trying to create planar quad meshes, and we're trying to get constant intersection angles, which is of course easy on a smooth surface where the lamellas would meet in a plane and you can measure that angle. But of course, in a discrete sense, that's a little more complex. So I'm going to talk a little bit about this checkerboard approach, about controlling the angle and the planar quad meshes, and then I'm going to talk about asymptotic nets and their practical implementation. So the approach is actually pretty straightforward, that even I think understand it. By just adding the midpoint of a quad, you can create a parallelogram, and that is already a planar quad. So that's a very straightforward way to have basically to turn any quad mesh into a semi-planar quad mesh by doing this edge midpoint subdivision. And this is basically what we're doing here. We're just also adding the general diagonal. So we get a lot of meshes out of this. We have in yellow the original quad mesh. Then we have this checkerboard pattern in blue and white. And then we also have the diagonal, diagonal meshes in red and blue, and we can measure the angle between those. And so with this is just a very simple and straightforward approach to optimize this mesh. And for example, the first thing we can do is by creating planar quad meshes for the red and blue, then also the white quads are planar, and then we can get a series of planar quad meshes in all these checkerboards, where the checkerboard itself is slightly less fair. You can see a little wiggle there. The next step that you can do with this is control the angle. And before that was only possible with circular meshes or conical meshes, and now it's a pretty straightforward approach by just measuring the angle between the red and blue diagonals. And this can be applied to any surface, and so you can get this planar quad almost a square mesh along the principal curvature lines. Then the third benefit is that comes with any principal curvature mesh, I guess, is this torsion-free nodes. So neighboring discrete normals are coplanar, as you can see here, and that has great benefits for the support structure in architecture. So you can have these torsion-free nodes where all the lamellas meet in one axis. Now we can access these things. We can also access different angles by controlling the length of these diagonals. So we don't only aim for orthogonal meshes, but we can aim for any other angle. And I'm going to skip to that. Here are some examples of these planar quad meshes that are only restricted to isothermic surfaces. And here's an architectural illustration of that. And here are some examples of now constant angle with planar faces that are not 90 degrees. So here you see some 60-degree meshes. And I would like to now jump to the second part of this. Because we have these diagonal meshes, we can also access the diagonal part to the principal curvature mesh, and that is the asymptotic mesh. So why are we interested in these asymptotic grid shells? I personally got very interested in them because of construction reasons, right? So we can build them from straight and flat strips of material that can just be cut out of sheet material or even taken from the lamellas that we order. And we can use the elastic deformation to create doubly curved grid shells. And the great thing here is that we have a strong axis that remains strong and doesn't change curvature, and it remains normal on the grid, so it can take normal loads like wind. And we have a weak axis that can be used during assembly and during construction to change the geometry from flat into this double curved design. And we can also achieve orthogonal nodes, that is on minimal surfaces, and I'll get to that in a second. So we built this first pavilion in 2018 in Munich together with Dennis and Jonas, and that was presented at the last AAG. So let's quickly talk about asymptotics on a minimal surface. I think what we need to know is that these asymptotic curves follow a path of zero normal curvature. And if the mean curvature of a surface is at equilibrium, that means that the two principal curvatures are of the same absolute value, then these asymptotic curves are exactly at a right angle to each other. And that means because they follow a path of zero normal curvature, they actually create a planar vertex star, as you can see on the bottom. And this is also how we then access that in optimization. So we just have to create a planar vertex star, and then we can also create asymptotic meshes. And again, we can do that not only for a right angle, and then we create a minimal surface, as you can see here. So here you see both overlaid, the optimized surface and already the lamellas on top, and then we can just basically only produce these smooth lamellar curves. But we can not only do that for a right angle, but we can also do that for any other angle now, which is of course very powerful. So now let's go into the practical application of that. First thing is that we can just cut it from any sheet material with almost no offcuts. So that's just a material saving fabrication. And also, if we do a constant angle, we get these repetitive notches or repetitive node conditions. That's pretty straightforward for a desktop model, but when we scale it up to a larger scale, I think it gets more interesting and more challenging, because we have gravity and we have to solve other issues. For example, in timber, we cannot have them laid out in the same layer because of the slots where the timber would easily break. So we put them on 2 layers, and we also use 2 lamellas in order to create more rigid profiles. And there's a lot of work going into these joints, even though they're all the same now and simple. But because we want to access this possibility of a planar construction and then of a deformation into the double curved shape, that there's a lot of thought in going through that joint, how it can be rotatable and then fixable at 90 degrees. And our latest development here is this idea of having prefabricated sandwich lamellas, basically with 2 sheets of metal and a rubber inlay, and that allows us to still rotate this lamella, and the rubber acts kind of like a cartilage and bone system together with the steel. And then once we have the design shape in place, then we fix these stars and lock the 90-degree angle. So that looks like this. Here you can see it in flat state, and we can then push it into the doubly curved shape. And this is also, I'm going to talk about this transition, this mechanism at the end of this paper. So now we're not only interested in these 90-degree minimal surface nets, but we're also interested in any other angle here. So for example, we took this 60-degree asymptotic net and looked at how that could be used in a design here, for example, for a metro station, where this 60-degree angle might be of benefit to show the dynamic or to have structural orientation in the grid. And also we can control the angle very precisely. So we can really, for example, control a transition from 60 to 90, or reverse that from 90 to 60 degree. And what you see here, what really for us was quite exciting, is that there seems to be some sort of movement transition that we can even program into the net. So for this, I want to show a project that we did completed in 2019, where we also deliberately used this transition from a 90-degree angle to a 60-degree angle. And we activated that actually through this funicular form finding. Basically, we hung it upside down, but that geometry was pre-designed. But through pulling it up here at the back, we get this narrowing of these angles to approximately 60 degree. And here you can see one of those modules prefabricated. We then attached 4 of those on site. These are my kids and my wife here. Look at the site visit, and finally attached a membrane on top. And here you can see this transition, and we did that really for the structural benefits of having the lamellas oriented more towards the supports. And my final example, which is also presented in paper number 6 by Jonas Sikore, is our latest development, the kinetic umbrella that we will build in July in Munich. And here we are using this shift of angles really deliberately to create a kinetic mechanism. So we can really change the shape of this mesh from approximately 0 to approximately 90 degrees, and by that we can activate transformation. And by choosing the right number of constraints, this is an almost a linear mechanism. And again, the main development here goes into the joints and what kind of elasticity and yield strength can the material give us, and how can we create this rotation in the joints, but at the same time fix an angle when we need to. This is a really interesting overlap of geometry. I'm now approaching it from this geometric side, but Jonas is approaching that at the same time from the mechanical side in his paper. So please have a look. Thank you.
Thank you, Eike. If I may say, I think you were a very worthy replacement for Helmut. So thank you very much for this summary. As usual,
the formulas, I don't know if you noticed that.
As usual, please post your comments in the chat, or for the brave, you can walk onto the stage. We would welcome you very much up here as well. Very, very fascinating work. I'm curious about, so when you talk about the asymptotic grid shells at various angles, does that always mean you have some sort of mechanism structure? Or, I mean, are they, like, if you optimize for 60 degree, can you deform it into something with 90 degree, or are these rigid structures?
Oh, but yeah, that's a good question. I have to say that. Oh, where's the echo coming from?
Xavier, I think we got some echo from you. Okay.
I think that is that's going to be our next paper. If we right now we could create these transitions, right? But we haven't really actively looked geometrically at really creating the full family of grids there, right? So I work together with Kai Gui to just show some transitions, but we haven't really deepened them. But I do think, I'm quite certain that we can use that to actually geometrically steer the kinetic behavior, right? That's what you're asking. But we haven't done that in this paper, and this will be, I think, the next paper. But we just saw that there is this similarity. But for our design, we did it from the mechanical side, and we just actually modeled the lamellas and watched how they would deform.
Right.
But I can answer the question. I'm sure, yes, there's always a mechanism. It's just if you take these lamellas and you put them together, and I've built a lot of models, they always are movable. Actually, they're too movable, right? So we have, if you just take a grid. Actually, let me get this really quickly.
So nothing better than a physical model.
Yeah, so we built this hyper, right? Which is a really nice. This is just a double ruled surface, right? And then you can planarize it, and if you bend it further, it actually turns into an NEPA minimal surface. So it has the same length edges as the hyper. We just realized that through this model, but when I built it, I thought, great, I'm going to show this. But then actually, when you hold this in your hand, it's super, super soft and weak, right? So you need as few extra constraints in this. So here, the solution would actually be to just hold this cross at 90 degree, and then we could still activate this mechanism, but we would have that kind of constraint in the system. And we did that now for this one, which is now completely 90 degree. And equilateral asymptotic net, and that should be now a pseudosphere because if all the lengths are constant in an asymptotic net, that should mean actually that the Gaussian curvature also remains constant. Of course, I haven't measured this. I just tested this on this model. But here now you can see there's not so much wiggling because I'm holding these these inner bars at 90 degrees, and the outer ones are modeled with hinges. So I can just 3D print these different nodes and just test and play with this.
Yeah, this is fascinating. I mean, it actually it reminds me when we started our work on the X shells. This was actually inspired by a friend of mine who built one of these structures, and he was actually surprised that it collapsed. You know, he wanted to build a double curved structure, but it was like a grid shell, and then it collapsed. It had a mechanism built in, and he didn't expect it, and it was actually kind of something he didn't want to have. But then it raised a lot of interesting questions, right? So sometimes, I mean, this deployability, I think, is very interesting for construction. But of course, it means you have to, potentially stiffen the surface or control the deformation in some other way.
Yeah. I wanted to we also stumbled upon it, just to share that when we built our first prototype in timber. First thing I always build in timber, and we did that actually spatially. So all the lamellas were actually, we had chairs and propped up, and we assembled them in space with these knots, because we didn't know that it was possible to do that flat, right? And then we had the timber model, and we I can stop sharing already. And one day we had the timber model on the table, and we just pressed on it, and we noticed we could just push it flat, and it would just pop up by itself again. So it's the model of the same prototype that I just showed. And then after that, we realized, okay, let's try it with having these flexible nodes for the next prototype. Yeah.
Yeah, this makes perfect sense. I mean, I think there's several people. I think there's a group in Barcelona who worked on these geodesic grid shells as well, and I think they stumbled upon this. Yeah, Enrique. I think they stumbled upon this in a similar way. So I think but which just shows that sometimes building these physical models and playing with them, because it's not obvious, that these mechanisms are there and that they would work out in this way. I think one can really gain some intuition and understand some problems that then can lead to interesting research.
Yeah.
So the project for Munich is your next physical goal, but do you have anything beyond that? Is there some interest? You built this architectural structure in Ingolstadt, but are there other projects on the horizon to scale it up even further?
So there's no clients yet. The one in Ingolstadt was great, right? Because we were actually approached because they saw it and they wanted that for their design hotel. But I think here in Hong Kong, what I'm pushing right now is this idea of not always going into this grid shell, which is like, it's a sexy topic, but maybe it's not as applicable actually in architecture that often. So I'm looking here at this facade modules, and this is something that you just caught a glimpse of, and I showed the joint for that. This is this module. So the idea more about can we integrate this in the built environment? Can there be a completely normal transom mullion facade, right, rectangular, and we can actually use this asymptotic net to kind of transition from this flat grid into a curved grid and back into a flat grid? Because that's actually the nice thing about these asymptotes, that when you are flat, they actually kind of behave, right? They follow the edge curves, and when you curve, when you have a curved surface, then they start diagonalizing, and so it's actually a really cool tool to create this transition.
But so there you would also be looking at dynamic facades or static structures?
No, there's just static, and I'm more looking now at panelization. So the nice thing is that we can create these isothermal webs. This is actually a different presentation. I'm not going to pull this up now. It's a different paper. But so we're looking at these isothermal webs because we can use the asymptotic nets for the substructure, but then we still have the principal curvature lines as the perfect diagonals, so we can have planar quads on top, or we can have developable strip facade. So we can basically mix and match there pretty nicely.
Very interesting. We still have a few minutes, and all the speakers are on the stage, so I want to encourage the audience to maybe post a few more questions either on the chat I think we should at least have one person who dares to come up on stage. No,
I agree.
Don't be shy.
We can call them out. We can see them.
That's right. There should be a tool to just pull them up on stage, right? Literally just beam them up there. Okay, but I would also, I mean, I want to open the floor also to Davide and Xavier and I could to ask questions maybe to each other, right? I think these papers have really interesting connections. And if you guys have some questions or ideas for, oh, somebody's walking onto the stage. So great.
It's 30 seconds delay again.
Hi, can you hear me?
Yes, we can. Please go ahead.
Hi, Eike, grüß dich.
I can't see you though.
Sorry, I don't have a camera because
Oh,
I'm
no
on
problem.
my
No
work
problem. I'm glad you
computer.
Yeah.
So this checkerboard pattern is quite nice realization, right? When you have these paraboloids all over a four-side panel mesh, and then I mean, that's easy for me to understand for someone who isn't too deep into the mathematics. But then the next step, when you operate on the white panels of the checkerboard, is there some literature or some easy, let's say, way to explain it so that maybe I can operate on the original model in a kangaroo model or something where I have some fixed constraints, and then I can just with the empirical knowledge and not really the higher mathematics that escape me, that I can recreate these processes.
I think this paper would now be a good starting point for that, because you can model you can do the edge midpoint subdivision, right? That's it's straightforward, and then you have the parallelograms, and then you can draw the diagonals, right? And then you can just set I guess that you can do that in Kangaroo, or so you can just say 90 degree or have some length constraint, and so that should actually lead to usable results. I have to say I didn't try it that way because we have Helmut doing it numerically, but I guess it should work the same way then.
Okay, so that means, if I understand correctly, that then I have to operate on my first mesh to get the diagonals with a 90-degree angle. So my first mesh is kind of not defined from the first step, is it?
Yeah, I'm hard to understand what you mean by first mesh.
No, the yellow one on the paper, I'm sorry, without the visuals is quite hard to explain.
Yeah, I'm pulling it up right now. So the initial mesh is the yellow one, right?
Yeah, right.
And you can control these white checkerboards. That was your question. You control them via these blue and red diagonals. If they fulfill a certain constraint, for example, that they're 90 degree to each other, and that they are planar, for example, that if the red one is planar, then the white one will also be planar.
Okay. So then that more or less answers the question that I asked, because if on the beginning the yellow one isn't giving me the 90 degrees between the red and the blue one, that means I have to operate on the yellow one in order to get the 90 degrees between the red and the blue.
You can see that. I mean, you have to operate on all of them at the same time.
Yeah.
Depends which ones you take.
I think what the question is really getting at is, for you guys to release the code and make it accessible as a Grasshopper plugin.
Okay. I actually always ask Helmut to do that too for me. so
there you go.
But there's 3D models to be sent over. So yes, I'm going to pass that on.
Sure. I mean, I don't mean that I want to get a black box that I don't understand. I'm really just asking because I want to get a little bit deeper on it, and really it's quite nice. Maybe I just have to sit on it a little bit more time. Even with the asymptotic one, I mean, on the paraboloid is quite easy, but on these different surfaces, then yeah, you really have to, I guess I really have to read up on it a little bit more. But thanks, it was really
I think this
enlightening.
is, thanks for the question, Ricardo, because I think this is the time for me to do some commercial again. We just ran a 2-day workshop on how to use Bowerbird, free plugin for Rhino. You can just download it for Grasshopper, and Kiwi to design these asymptotic networks. And so Bowerbird has this pathfinder where you can just set the normal curvature or the torsion. So you can set it to 0, and then you get asymptotic curves, or you can set the torsion to 0, then you get the principal curvature lines, or you can set it to any other value, and it will find the path on a smooth surface. So it's a very powerful tool for designers like you and me.
Okay, that's quite cool. And if I wanted to do one myself, I could theoretically also analyze points along the surface for the principal curvatures, and then with the directions of both principal curvatures, then I can also more or less get the asymptotic, right?
Yep, yeah. You can also directly analyze the asymptotic directions.
You know, I mean, to see every step will be much more enlightening for me. Something that I haven't tried. I mean, thanks a lot. This was really, really great and motivational for me to try to get into the higher.
The material of the workshop is also publicly available, I think. I'm going to ask Cyril if he can post that again.
Oh, cool. On the Thinkshell page?
I think so. I'll ask him to say that publicly. It was all recorded anyway. Yeah.
Okay. Thanks, Sean.
Normally, the result of the workshop will be in the workshop area. If you provide a link.
Okay.
That's the project. So.
But I think, I mean, what Ricardo was asking is also, I mean, one of the aspects of this paper in particular is actually the fact that this geometric construction is quite accessible and quite simple, right? I mean, and at the same time, very powerful. So I think with something like Kangaroo, you might be able to implement some of these constraints, right? The angle constraints and the planarity constraints. So I think it might actually not be too hard to set something up that would solve for such a system. I think maybe Davide wanted to ask a question earlier.
Yes, I have a question for Xavier. I wanted to know, because his work is on isotropic space, and I would like to know if there is some connection between the Ingarten surfaces and in the Euclidean case. So maybe when we have stresses that are along the Euclidean principal curvature directions, as we know, in this case, we can have a simplified substructure, for example.
Okay, so mostly about the how do the mechanics properties would transfer, and what properties will you keep going from isotropic to Euclidean?
Yeah, if there is, I don't know, some chance to classify these kind of surfaces, if you have some idea about that, or there is some Euclidean somehow counterpart on this work.
Oh, I don't know about classification, but yes, they are strongly related. They will work on how they were related by Helmut. He could have talked about this, about how you actually can deform these surfaces in a uniform setting by looking at the Gauss map you are using to describe the curvature. Like in the Euclidean geometry, you would use the sphere as your Gauss map, and that would naturally give you forces that correspond to pressure, normal pressure forces that are normal to your surface, and you would get stress line aligned with principal curvature lines. And as you would deform your Gauss map in an affine way all the way until parabola. You end up in isotropic geometry, in which you have these isotropic principal curvature lines that get aligned with principal stresses for the special case of now a vertical pressure load. So yes, they are strongly related, and I think like one way to see in the transition between the two and to regroup them would be by looking at their ghost map. And but from a mechanical point of view, as you would do this deformation, actually you would get into like loadings that would not make sense in practical way. So that's this. I mean, as engineers, we're interested in having a vertical pressure, vertical force, or normal pressure. We will not be interested into the weird load case that you would have in between.
Thank you.
Yes, and for me, on a final, on a little note on the work that you presented, I think it's quite, it's fascinating how we're able to recover with this model the crossing angle between polylines. That's something that you think you would lose completely as you go from a smooth net of curve into a discrete mesh, like the intersection between two lines, and you show that actually, okay, just look at the diagonal of this mesh, and you can recover the crossing angle appears, and you actually get a way to a different look at objects that we thought we already know. Like for example, having planar quadrangles with, that are nearly rectangular. Like there was these beautiful models from circular meshes, conical meshes, and here you have another point of view at them that also appears to be more effective computationally. So that's fascinating work.
Mm-hmm. Thank you. Thanks to Helmut.
Great. Any more questions from the audience? I don't see anything in the chat right now. Well, if that's not the case, I mean, we have another day of conference, of course, where you can all try to catch hold of any of the authors and ask them questions. Maybe it's easier to do in a private corner on the floor. I really want to thank you all for presenting this amazing work. I think this is a fantastic session and a fantastic collection of papers. And yeah, I want to encourage everyone else to also once in a while dare to step up on stage. Maybe in a session tomorrow, it's not that difficult. We're nice people up here.
Mark did it before, right?
That's right. I wanted to set an example.
Yes.
But anyway, I think I thank you all, and there's more time to hang out now. I believe there's no more official program point tonight, right? And the conference program starts tomorrow again, but you can, of course, still hang out and talk to people and, grab a virtual drink and enjoy the discussions. Mm-hmm. Thank you very much.
Thank you.
Thank you.
Thank you.